Time travel. The very concept evokes wonder, curiosity, and perhaps a touch of fear. For as long as humans have been aware of time's passage, we have dreamed of mastering it, bending it to our will, escaping its one-way flow. This fascination transcends cultures, generations, and centuries, embedding itself deeply in our collective imagination and scientific pursuits alike. Consider for a moment what it would mean to journey through time, to witness the building of the pyramids, to meet your ancestors, or to glimpse the fate of our planet thousands of years hence. These thoughts aren't merely flights of fancy. They represent humanity's deepest yearning to transcend our most fundamental limitation, our imprisonment in the present moment. The concept of time travel first captured widespread public imagination in the late 19th century with H.G. Wells' groundbreaking novel, The Time Machine. Published in 1895, this seminal work introduced millions to the concept of a vehicle that could transport its occupant backwards and forwards through time at will. What made Wells' approach so revolutionary was its attempt to provide a seemingly scientific basis for what had previously been the domain of pure fantasy. Since then, time travel has become a staple of our cultural landscape. From the whimsical adventures in Back to the Future to the mind-bending complexities of Interstellar, from Doctor Who to Avengers Endgame, these stories have shaped how we conceive of temporal journeys. They've popularized concepts like paradoxes, alternate timelines, and the butterfly effect, ideas that originated in serious scientific and philosophical discourse, but found their way into our everyday vocabulary through the power of storytelling. But there's a profound difference between the time travel of fiction and the possibilities suggested by actual science. In movies and books, time machines often work by mysterious mechanisms requiring little more than the flip of a switch or the press of a button. The real science of time, however, reveals a far more nuanced and fascinating picture, one where time itself is not the absolute universal constant we intuitively believe it to be. This is where our journey truly begins, because remarkably, when we look at the equations governing our universe, particularly Einstein's theories of relativity, we find that they do not forbid time travel outright. In fact, they suggest that time is far more flexible and potentially manipulable than our everyday experience would lead us to believe. The fixed rate at which time passes in our daily lives is, it turns out, something of an illusion, a convenient approximation that breaks down under extreme conditions. Scientists have already confirmed that time can be dilated, made to run at different rates depending on speed and gravitational forces. Astronauts returning from the International Space Station have aged ever so slightly less than they would have had they remained on Earth. GPS satellites must constantly adjust their clocks to account for time passing differently in orbit than on the ground. These aren't theories, they're measurable facts about how our universe operates. So, if time can be stretched and compressed, what other manipulations might be possible? Could the mathematics that allows for time dilation also permit more dramatic alterations to temporal flow? Could we find or create conditions extreme enough to bend time back upon itself, creating closed loops that would allow travel into the past? These questions aren't merely academic. They strike at the heart of our understanding of causality, free will, and the fundamental nature of reality. If time travel to the past were possible, it would force us to reconsider our most basic assumptions about how the universe works. Can effects precede their causes? Can the future influence the past? Can paradoxes exist in physical reality? The quest to answer these questions has led physicists to explore some of the most extreme environments and phenomena in our universe. Black holes, where gravity becomes so intense that it warps the very fabric of space-time. Wormholes, theoretical tunnels connecting distant regions of space and time. Cosmic strings, hypothetical defects in space-time that could potentially be harnessed for temporal manipulation. As we embark on this exploration of time travel's possibilities, we'll journey from the familiar world of our everyday experience to the mind-bending frontiers of theoretical physics. We'll examine what current science tells us about the nature of time, and how that knowledge might someday be applied to the prospect of temporal voyages. We'll confront the paradoxes and problems that arise when we contemplate visiting the past and consider whether these challenges are truly insurmountable. For while time travel remains firmly in the realm of speculation, it is speculation informed by our best scientific understanding of how the universe works. The equations that have successfully predicted phenomena throughout the cosmos do not rule out the possibility of temporal journeys, and in some cases, they seem to suggest potential pathways to achieving them. To understand these possibilities, however, we must first confront a more fundamental question. What exactly is time? This seemingly simple query has puzzled philosophers and scientists for millennia. Is time an independent dimension, flowing uniformly throughout the universe? Is it an emergent property arising from other, more fundamental processes? Is it perhaps an illusion created by our own minds to make sense of a reality that works quite differently than we perceive? The answers to these questions form the foundation upon which any serious discussion of time travel must be built. Because before we can hope to manipulate time, we must understand what it is we're attempting to manipulate. And as we shall see, time is far stranger and more fascinating than most of us have ever imagined. The human preoccupation with time extends far beyond mere scientific curiosity. It reflects something fundamental about our consciousness, our awareness of our own mortality, of moments passing never to return. We are perhaps the only species on Earth that fully comprehends the inexorable forward march of time and its ultimate consequence, our own finite existence. This awareness has driven us to leave legacies, to create art that might outlast us, to seek ways of extending our lives, and yes, to dream of machines that might allow us to revisit the past or leap into the future. Time travel narratives often serve as powerful metaphors for our very human desires, the wish to undo mistakes, to revisit pivotal moments in our lives, to see what becomes of our descendants long after we're gone. When Marty McFly travels back to meet his parents as teenagers, or when the time traveler in Wells' novel journeys far into the future to witness humanity's evolution, they're enacting fantasies that resonate deeply with our own yearnings and fears. But these stories also reveal our ambivalence about temporal manipulation. Almost invariably, fictional time travelers discover that altering the past creates unforeseen consequences, that knowledge of the future becomes a burden, that trying to control time often leads to losing control of one's own destiny. These cautionary tales suggest that even as we dream of mastering time, we recognize the profound dangers such mastery might entail. Science fiction has given us countless mechanisms for time travel, vehicles powered by mysterious crystals or futuristic technology, wormholes connecting distant eras, mental projection across temporal boundaries. Some of these fictional devices bear at least a passing resemblance to genuine scientific speculations, while others remain firmly in the realm of fantasy. But all of them share a common aim: to make concrete and tangible the abstract notion of moving through time as we move through space. And this brings us to a crucial insight from modern physics. Time and space are not separate entities, but are intertwined in what scientists call space-time. This concept, emerging from Einstein's theories of relativity, revolutionized our understanding of the universe and opened new possibilities for considering time travel not as magical thinking, but as a potential consequence of the universe's structure. Prior to Einstein, most scientists followed Isaac Newton's conception of time as absolute, flowing at the same rate for everyone everywhere, a universal clock ticking uniformly throughout the cosmos. In this Newtonian universe, the very idea of time travel seemed absurd, a violation of time's essential nature as an immutable, linear progression. Einstein shattered this paradigm. His special theory of relativity, published in 1905, demonstrated that time is relative. Its passage depends on the observer's motion. His general theory of relativity, completed in 1915, showed further that gravity affects time, causing it to pass more slowly in stronger gravitational fields. Suddenly, time was revealed to be elastic, variable, responsive to physical conditions, and potentially manipulable under the right circumstances. These revolutionary theories didn't immediately suggest the possibility of time machines, but they planted the seed of the idea that would grow in the decades that followed. If time could be stretched and compressed, might it also be folded back upon itself? If gravity could slow time, might extreme gravitational conditions create paths through space-time that lead to the past? The first serious scientific proposal for a time machine came from Kurt Gödel, a mathematician and close friend of Einstein's. In 1949, Gödel found a solution to Einstein's field equations that described a rotating universe in which closed time-like curves exist, paths through space-time that return to their starting point in time as well as space. A traveler following such a curve could, in theory, return to their past. Einstein was troubled by Gödel's solution, believing it revealed a flaw in his theories rather than a genuine possibility. But Gödel's work opened the floodgates. In the decades that followed, physicists would discover numerous other solutions to Einstein's equations that permitted closed time-like curves and, by extension, travel to the past. Most of these theoretical time machines require exotic arrangements of matter and energy, rotating black holes, cosmic strings, negative energy, wormholes maintained by exotic matter with negative mass. None can be constructed with current technology, and some may violate other physical laws. But the fact that they emerge naturally from our best theories about gravity and space-time suggests that time travel cannot be dismissed as merely fanciful thinking. Meanwhile, travel to the future, at least in a limited sense, is not merely possible, but has been experimentally verified. The time dilation effects predicted by special relativity have been confirmed repeatedly, most precisely in particle accelerators, where subatomic particles moving at near-light speed decay more slowly than their stationary counterparts. An astronaut traveling at 99.5% of the speed of light for what seems to them like a one-year journey would return to Earth to find that about 10 years had passed. They would have, effectively, traveled 9 years into the future. Of course, this form of time travel is one way. The astronaut couldn't use the same method to return to their original time, and the energy requirements for sending macroscopic objects at such speeds make this approach impractical with current or foreseeable technology. But the principle has been firmly established. Future-directed time travel is physically possible. Past-directed travel presents far greater challenges, both practical and theoretical. Beyond the enormous engineering obstacles involved in creating something like a traversable wormhole or harnessing the energy of a rotating black hole, there are profound conceptual problems raised by the possibility of changing the past. The most famous of these is the grandfather paradox. If you traveled to the past and prevented your grandfather from meeting your grandmother, you would never have been born. In which case, how could you have traveled back in time to prevent the meeting? This apparent logical contradiction has led many to argue that time travel to the past must be impossible, regardless of what the equations suggest. Others have proposed various resolutions to the paradox. Perhaps the past cannot be changed. Any attempt to alter it would somehow be frustrated, preserving the timeline's consistency. Perhaps changing the past creates a new timeline, a parallel universe where events unfold differently. Perhaps the very act of traveling to the past creates a self-consistent loop where your intervention becomes part of the causal chain that led to your own existence. Each of these solutions raises its own philosophical and physical questions. Can free will exist in a universe where attempts to change the past are mysteriously thwarted? Do parallel universes actually exist, or are they merely a convenient mathematical construction? Can information or matter truly have no origin, existing in a perpetual causal loop? Compelling as these questions are, they remain largely theoretical. No one has yet detected a naturally occurring wormhole or cosmic string that might be used for time travel. No one has managed to create the conditions that would allow for the formation of closed time-like curves. The enormous energies required, equivalent to the mass energy of entire stars or even galaxies, place such experiments far beyond our current capabilities. Yet the door to time travel has not been definitively closed. Each year brings new insights into the nature of space-time, quantum mechanics, and the fundamental forces that govern our universe. Theoretical physicists continue to explore the mathematics of time travel, seeking loopholes in the apparent prohibitions and imagining technologies that might someday exploit them. Perhaps the most thought-provoking aspect of time travel research is what it reveals about the nature of time itself. If time travel is possible, even in principle, then time cannot be the simple, linear progression we intuitively experience. It must be something far more complex and nuanced. Perhaps a dimension as navigable as space. Perhaps a network of interconnected moments. Perhaps something we cannot yet conceptualize with our minds, evolved to perceive time in only one direction. Some physicists, like Julian Barber, go so far as to suggest that time as a flowing entity doesn't exist at all, that what we perceive as the passage of time is an illusion arising from the relationship between different states of the universe, what he calls time capsules. In this view, the apparent flow of time emerges from the way our brains process information, not from any fundamental property of reality. Others, like Lee Smolin, argue that time is not only real but fundamental, the primary reality from which space and matter emerge, rather than a secondary property of the universe. In Smolin's temporal naturalism, the passage of time and the emergence of new structures and phenomena are the essential features of our universe. These competing perspectives on time's nature remind us how much remains unknown about this most familiar yet mysterious dimension of our existence. And they highlight why the question of time travel is not merely a technological problem, but a profound philosophical and scientific inquiry that may ultimately transform our understanding of reality itself. As we continue our exploration of cosmic time travel, we'll delve deeper into these mysteries. We'll examine the empirical evidence for time's malleability, explore the theoretical possibilities for more dramatic temporal manipulations, and consider what these possibilities tell us about the universe and our place within it. For now, let us simply marvel at how far we've come in our understanding of time, from the rigid, absolute time of Newton to the flexible, relative time of Einstein, to the bizarre quantum time that seems to defy classical logic. And let us wonder at what further revelations await us as we pursue the tantalizing possibility that someday, somehow, we might break free from time's seemingly inexorable flow and navigate its currents as we now navigate the oceans and skies. To truly understand the possibilities of time travel, however, we must first grapple with a more fundamental question: what exactly is time? This apparently simple query opens the door to some of the most profound mysteries in physics and philosophy, and the answers, or lack thereof, will shape our understanding of whether journeying through time might ever become more than a captivating dream. To truly comprehend the possibility of time travel, we must first confront a deceptively simple question: what is time? Despite its fundamental role in our existence, time remains one of the most elusive concepts in science and philosophy. We experience it constantly, organize our lives around it, and yet struggle to define its essential nature. For most of human history, time was understood primarily through its measurement. Ancient civilizations tracked the movement of celestial bodies, creating calendars and clocks that divided existence into manageable segments. These early timekeeping devices, from sundials to water clocks, reflected a universal intuition. Time flows steadily forward at a constant rate, independent of human perception or physical conditions. This intuitive understanding of time was formalized in the 17th century by Isaac Newton, who described time as absolute, true, and mathematical, flowing uniformly without relation to anything external. In Newton's view, time was a cosmic metronome, ticking at precisely the same rate everywhere in the universe. Even if all matter, motion, and consciousness were removed from existence, Newtonian time would continue its relentless forward march. This conception of time dominated scientific thought for more than 2 centuries, until an obscure patent clerk named Albert Einstein revolutionized our understanding of the universe. In 1905, Einstein published his special theory of relativity, which contained a shocking revelation. Time is not absolute but relative. Its passage depends on the observer's state of motion. Einstein's insight stemmed from a simple yet profound observation. The speed of light is constant for all observers, regardless of their relative motion. This seemingly innocuous fact has extraordinary implications. If two observers are moving relative to each other, they must experience time differently to maintain the consistency of light's speed. Consider two observers, one stationary on Earth, the other traveling in a spacecraft at extremely high velocity. If both measure the speed of a passing light beam, both will record exactly the same value, 299,792,458 meters per second. This can only be true if time itself runs at different rates for the two observers. This isn't mere theoretical speculation. Highly precise atomic clocks placed on aircraft and satellites confirm that time passes more slowly for objects in motion compared to stationary ones. The effect is minuscule at everyday speeds. A passenger on a commercial airliner ages approximately 1 nanosecond less during a transcontinental flight than someone remaining on the ground. But as speeds approach that of light, time dilation becomes dramatically more pronounced. At 99% of light speed, time for the moving observer would pass at roughly 1/7 the rate experienced by a stationary observer. At 99.9% of light speed, the moving observer would experience time at about 1/22nd the rate of the stationary observer. The mathematics is clear. If we could travel at a significant fraction of light speed, we could effectively journey into Earth's future. A decade after his special theory of relativity, Einstein published his general theory of relativity, which revealed another stunning aspect of time. It is affected by gravity. Just as motion can dilate time, so too can gravitational fields. The stronger the gravity, the slower time passes. This gravitational time dilation has been confirmed by placing atomic clocks at different altitudes above Earth. A clock on a mountain runs slightly faster than an identical clock at sea level because the higher clock experiences slightly weaker gravity. GPS satellites orbiting 20,000 kilometers above Earth must compensate for this effect. Their clocks run approximately 45 microseconds faster per day than identical clocks on the ground. These revelations forced a profound reconceptualization of time. No longer could it be understood as an independent dimension flowing uniformly throughout the cosmos. Instead, time became part of a unified four-dimensional structure, space-time. In this framework, time and space are interwoven, with events occurring at specific coordinates in both spatial and temporal dimensions. The mathematician Hermann Minkowski, who had been one of Einstein's teachers, formalized this concept in 1908, declaring, "Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. This union, space-time, forms the backdrop against which the drama of the universe unfolds." In space-time, the familiar three dimensions of space, length, width, and height, are joined by a fourth dimension, time, to create a continuous manifold. Every object in the universe follows a path through this four-dimensional structure, what physicists call a world line. Even when an object appears stationary in space, it continues moving along the time dimension, tracing a straight line through spacetime. The geometry of spacetime is not fixed or flat, but can be curved by the presence of mass and energy. Massive objects like planets, stars, and black holes create wells or distortions in the fabric of spacetime. These distortions affect not only the paths of objects moving through space, but also the flow of time itself. Near a black hole, where spacetime curvature becomes extreme, time dilation reaches extraordinary levels. At the event horizon, the boundary beyond which nothing, not even light, can escape, time essentially stops relative to a distant observer. If we could somehow hover just outside a black hole's event horizon, ignoring the crushing gravitational forces that would make this physically impossible, we would witness the entire future history of the distant universe unfold before our eyes, while for us only moments would pass. This relativistic conception of time reveals why we cannot speak meaningfully about what is happening now across the vast reaches of space. Events that appear simultaneous to one observer may occur at different times for another observer in motion relative to the first. The very notion of now becomes observer-dependent, losing its absolute character. This relativity of simultaneity further undermines our intuitive understanding of time as a universal flow. There is no cosmic now marching uniformly forward throughout the universe. Instead, different observers will slice space-time differently, depending on their state of motion. Yet despite these revelations about time's relative nature, a fundamental asymmetry persists: the arrow of time. While the basic laws of physics work equally well whether time runs forward or backward, our universe exhibits a clear directional preference. Eggs break but don't unbreak. Coffee cools but doesn't spontaneously heat up. We remember the past but not the future. This temporal asymmetry is typically explained through the second law of thermodynamics, which states that the total entropy, roughly speaking, the disorder or randomness of an isolated system, always increases over time. When you drop a cup and it shatters, you're witnessing entropy in action. The ordered arrangement of molecules in the intact cup transforms into the disordered arrangement of the broken pieces, and the process doesn't spontaneously reverse. The arrow of time points in the direction of increasing entropy. But why did our universe begin in a low entropy state to begin with? Why wasn't the cosmos born in a state of maximum disorder, with entropy having nowhere to go but down? This question remains one of the great unsolved mysteries in physics, touching on the very origin and fate of our universe. Some theorists, like Ludwig Boltzmann in the 19th century, proposed that our perception of time's direction might be a statistical fluke, that in an eternal universe, random fluctuations would occasionally produce regions of low entropy that would then increase, creating the appearance of time's arrow. Others, like Roger Penrose, have suggested that the arrow of time is fundamentally connected to the expansion of the universe or to quantum effects in gravitational fields. The mystery deepens when we consider time at the quantum level. Quantum mechanics, our best theory for describing the behavior of matter and energy at subatomic scales, presents a picture of time that differs dramatically from both our everyday experience and the relativistic framework of Einstein. In the quantum realm, time appears in some ways more rigid than in relativity. Quantum mechanics generally treats time as a parameter rather than an operator. We cannot measure time in the same way we measure position or momentum. This has led some physicists to suggest that time might not be fundamental at all, but emerges from more basic quantum processes. Quantum phenomena also challenge our understanding of causality, the principle that causes precede their effects. Experiments like the delayed choice quantum eraser suggest that future measurements can, in a sense, influence past events. While these experiments don't allow for the transmission of information backward in time, thus preserving causality in a practical sense, they hint at a reality where temporal ordering may be more flexible than we imagined. The tension between quantum mechanics and general relativity comes to a head in extreme environments like the interiors of black holes or the first moments after the Big Bang. In these regimes, both theories are needed, yet they provide contradictory descriptions of reality. This incompatibility has driven the search for a theory of quantum gravity, a unified framework that would reconcile these two pillars of modern physics. Several candidates for such a theory, including string theory and loop quantum gravity, offer radical reinterpretations of time. Some suggest that time emerges from more fundamental quantum processes. Others propose that at the Planck scale, the smallest measurable length, approximately 10 to the power of -35 meters, space-time itself breaks down into a quantum foam of fluctuating geometry. In loop quantum gravity, time may be quantized, existing in discrete units rather than flowing continuously. If this proves correct, there would be a fundamental limit to how finely we could divide time, just as there appears to be a limit to how finely we can divide matter. These theoretical speculations remind us how far we are from a complete understanding of time. What seems clear, however, is that time is not the simple, flowing river of our intuition. It is stretchable, variable, inextricably linked with space, and perhaps emergent from deeper quantum realities. This complex nature of time has profound implications for the possibility of time travel. If time were truly the absolute universal flow that Newton described, time travel would be conceptually impossible, like trying to swim against a current that carries everything at precisely the same rate. But in a universe where time is relative, where its passage depends on motion and gravity, where space-time can curve and potentially connect distant regions, the possibility of temporal journeys cannot be so easily dismissed. Einstein's equations, in fact, allow for solutions that include closed time-like curves, paths through space-time that return to their starting point in time, as well as space. A person following such a curve could, in principle, return to their past. Whether such curves could ever be created in practice, and whether additional physical laws might prevent their formation, remains an open question at the frontier of theoretical physics. The philosopher of science Karl Popper once remarked that the flow of time is the most fundamental feature of our experience of the world. Yet modern physics suggests that this fundamental feature may be neither as uniform nor as unidirectional as our experience indicates. Time, it seems, is not a river carrying us inexorably forward, but a landscape we might someday learn to navigate in multiple directions. As we continue our exploration of cosmic time travel, we'll build upon this understanding of time as a dimension of space-time, a dimension that, while usually perceived as flowing in one direction at a constant rate, can be stretched, compressed, and perhaps even folded back upon itself under the right conditions. The question remains, how might we create or harness those conditions? What physical mechanisms might allow us to manipulate time more dramatically than the subtle dilations already observed? To answer these questions, we must delve deeper into the physics of extreme environments, places where space-time becomes so distorted that our everyday intuitions about time break down completely. But before we explore these exotic possibilities, let's examine more closely the time dilation effects that have already been confirmed experimentally. For these effects, subtle as they may be in our current technological context, represent the first small steps toward mastering time, and perhaps, eventually, traveling through it. Time dilation is not just a theoretical curiosity, but a measurable reality with practical consequences. Every time you use GPS navigation, you're benefiting from engineers' understanding of both special and general relativistic time dilation. Without accounting for these effects, GPS would accumulate errors of about 10 kilometers per day, rendering the system useless. Similarly, particle accelerators like the Large Hadron Collider routinely deal with time dilation. The particles circulating in these machines travel at more than 99.99% of light speed, experiencing time at a rate thousands of times slower than the laboratory environment. Unstable particles that would normally decay in microseconds can survive much longer from their perspective, allowing scientists to study them in detail. These practical applications of time's relativity remind us that what once seemed like abstract theoretical physics can have profound real-world implications. The same might someday be true for more exotic temporal phenomena. Today's theoretical speculation about wormholes or closed time-like curves might become tomorrow's technological breakthrough. Understanding time as a dimension of space-time is crucial for contemplating the possibility of time travel. Just as we can move freely through the three spatial dimensions within practical constraints, the question becomes, why can't we move freely through the time dimension? What fundamental physical principles, if any, prevent us from navigating time as we navigate space? The answer may lie in the unique asymmetry of time within space-time. Unlike the spatial dimensions, which allow movement in multiple directions, time appears to permit movement in only one direction at a constant rate. This asymmetry is not clearly explained by Einstein's theories, which treat time and space as components of a unified whole. Some physicists speculate that this temporal asymmetry might be linked to the expansion of the universe, or to quantum effects not captured in classical relativity. Others suggest it might be an emergent property rather than a fundamental aspect of reality, arising from the statistical behavior of enormous numbers of particles rather than from basic physical law. Whatever its origin, this asymmetry appears to be a defining feature of our universe, one that presents a formidable obstacle to the prospect of time travel, particularly travel to the past. Yet the fact that time can be dilated by motion and gravity hints that this obstacle might not be insurmountable. If time's flow can be altered, might it also be reversed under sufficiently extreme conditions? To explore this possibility, we must venture beyond the relatively mild distortions of space-time we've observed thus far, and consider environments where gravity becomes so intense that the very fabric of reality begins to tear. Environments like the vicinity of black holes, where time and space exchange roles, and the conventional rules of causality struggle to maintain their grip. As we transition to our exploration of time dilation and its implications, we carry with us this understanding. Time is not absolute, but relative, not independent, but intertwined with space, not rigid, but flexible. And in this flexibility may lie the key to unlocking time's deepest secrets, and perhaps, someday, to traveling through its mysterious dimension in ways our ancestors could scarcely have imagined. Having explored the nature of time as a dimension interwoven with space, we now turn to one of the most fascinating and experimentally verified aspects of Einstein's theories: time dilation. This phenomenon, the slowing of time due to motion or gravity, represents humanity's first tentative steps toward manipulating the flow of time. Time dilation isn't science fiction. It's a measurable reality that affects everything from subatomic particles to astronauts in orbit. And while current technology doesn't allow us to exploit these effects for dramatic temporal journeys, understanding time dilation provides the foundation for contemplating more ambitious forms of time travel. Let's begin with the time dilation caused by motion, first predicted by Einstein's special theory of relativity. The principle is straightforward yet profound. The faster an object moves relative to an observer, the slower time passes for that object from the observer's perspective. This effect becomes noticeable only at speeds approaching that of light, 299,792 meters per second, which is why we don't perceive it in our everyday lives. Imagine two identical clocks, perfectly synchronized. One remains on Earth, while the other is placed aboard a spacecraft. As the spacecraft accelerates to extreme velocities, something remarkable happens. From the perspective of observers on Earth, the clock aboard the spacecraft appears to tick more slowly. If the spacecraft could somehow reach 99.5% of light speed, each year passing on the moving clock would correspond to about 10 years on Earth. The crew of this hypothetical spacecraft would experience time normally from their perspective. They wouldn't perceive their movements as sluggish or their thoughts as coming slowly. Only when comparing their clock to Earth's would the discrepancy become apparent. They would be aging and experiencing life at a normal rate. But upon returning to Earth, they would find that much more time had passed for those left behind. This isn't merely theoretical. Subatomic particles called muons, created when cosmic rays strike Earth's upper atmosphere, provide natural evidence of time dilation. Muons are unstable, typically decaying after about 2 microseconds. At the speeds they travel, more than 99% of light speed, they should only be able to travel about 600 meters before decaying, even accounting for their tremendous velocity. Yet muons created high in the atmosphere routinely reach Earth's surface, traveling distances of 10 kilometers or more. The explanation? From our perspective, time passes more slowly for these rapidly moving particles. Their internal clocks run at about 1/15 the rate of our laboratory clocks, extending their lifespan just enough to reach the ground before decaying. From the muon's perspective, if such tiny particles could have perspectives, the distance they travel appears contracted due to another relativistic effect, allowing them to make the journey within their own brief lifetime. Scientists have also directly measured time dilation using incredibly precise atomic clocks. In 1971, Physicists Joseph Hafele and Richard Keating placed cesium atomic clocks aboard commercial jetliners and flew them around the world, then compared their times with identical clocks that remained at the United States Naval Observatory. The airborne clocks showed small but measurable differences that matched Einstein's predictions. More recent experiments using even more precise clocks have confirmed these results with greater accuracy. In 2010, researchers at the National Institute of Standards and Technology demonstrated time dilation at walking speeds, showing that raising an atomic clock by just 33 centimeters caused it to tick ever so slightly faster, by about 90 billionths of a second over a 79-year lifetime. But motion isn't the only factor that affects time's passage. Einstein's general theory of relativity revealed that gravity also dilates time. The stronger the gravitational field, the slower time passes within it. This gravitational time dilation complements the effects of special relativity, creating a more complete picture of how time can be manipulated. Every massive object in the universe creates a gravitational field that distorts the fabric of space-time. This distortion affects not only the paths of objects moving through space, but also the flow of time itself. The closer you are to a massive object, the slower time passes relative to regions of weaker gravity. On Earth, this effect is subtle but measurable. Time passes slightly faster at higher altitudes than at sea level because the gravitational field weakens as distance from Earth's center increases. For every kilometer of altitude, clocks run approximately 3 parts in 10 to the power of 13 faster, an infinitesimal difference in human terms, but crucial for technologies like GPS that require nanosecond precision. GPS satellites orbiting at altitudes of about 20,000 kilometers experience time at a rate approximately 45 microseconds per day, faster than clocks on Earth's surface, due to weaker gravity. Simultaneously, their orbital velocity of 14,000 kilometers per hour causes time to slow by about 7 microseconds per day due to special relativistic time dilation. The net effect is that satellite clocks run about 38 microseconds per day faster than ground-based clocks, a tiny difference that would nevertheless cause navigational errors of about 10 kilometers per day, if not accounted for in the system's design. More extreme gravitational environments create more dramatic time dilation effects. Near a black hole, where gravity reaches its maximum possible intensity, time dilates to extraordinary degrees. At the event horizon, the boundary beyond which nothing can escape a black hole's gravitational pull, time would appear to stop completely from the perspective of a distant observer. If an astronaut could somehow survive near a black hole's event horizon, ignoring the lethal tidal forces that would actually tear them apart, they would experience time normally from their perspective. But for observers watching from a safe distance, the astronaut would appear to move in extreme slow motion, eventually freezing in time as they approach the horizon. This bizarre behavior results from the extreme curvature of space-time near black holes. The gravitational field becomes so intense that it drastically alters the geometry of space-time, creating conditions where light itself struggles to escape and time slows dramatically relative to distant regions. The 2014 film Interstellar depicted this phenomenon when astronauts visited a planet orbiting near a black hole called Gargantua. Due to the intense gravitational field, each hour spent on the planet corresponded to 7 years passing on their orbiting spacecraft, and even longer on Earth. While the film took some creative liberties, its portrayal of gravitational time dilation was based on solid physics, with noted theoretical physicist Kip Thorne serving as a scientific consultant. These two forms of time dilation, from motion and gravity, combine to create what physicists call the twin paradox. One of the most famous thought experiments in relativity. Imagine identical twins. One remains on Earth, while the other embarks on a journey to a distant star at near light speed. When the traveling twin returns, they would be significantly younger than their Earth-bound sibling. This isn't actually a paradox in the logical sense, though it was initially perceived as one. The apparent contradiction arises when we forget that the traveling twin undergoes acceleration and deceleration, breaking the symmetry between the twins' experiences. The traveling twin experiences a genuine shift in their time frame relative to Earth's. If such a journey were technically feasible, it would represent a form of one-way time travel to the future. The traveling twin would effectively skip ahead in Earth's timeline, experiencing far less time personally than passes on Earth. Several minutes or hours for the traveler might correspond to decades for those left behind. This possibility has led some to propose suspended animation as a potential method for future space exploration. If humans could be placed in some form of biological stasis, they might survive journeys to distant star systems that would otherwise require multiple generations to complete. The crew would age minimally during transit, effectively traveling to both a distant location and the future simultaneously. But what about the people left behind? Could they perceive or interact with the time-dilated travelers? The answer reveals another fascinating aspect of relativistic physics. From our perspective on Earth, we would see time passing extremely slowly for the near light-speed travelers. If we could somehow observe them directly, their movements would appear stretched out to an extreme degree, with each second of their time corresponding to many hours or even years of our time, depending on their velocity. Electromagnetic signals sent from the travelers, radio transmissions for instance, would be dramatically redshifted, their frequencies lowered to potentially undetectable levels. A normal voice transmission might be stretched into a growl so deep and slow it would be imperceptible to human ears. Conversely, from the traveler's perspective, events on Earth would appear to be happening at an accelerated rate. Radio signals from Earth would be blue-shifted to higher frequencies. They would receive hours or years of Earth's broadcasts compressed into minutes or seconds of their experienced time. This bidirectional effect highlights an important point about time dilation. It's always relative. There's no absolute or correct time frame against which others can be measured. Both perspectives, the Earth-bound observers and the travelers, are equally valid within the framework of relativity. The time dilation effects we've discussed so far are well established scientifically and have been experimentally verified. They represent the first tentative steps toward manipulating time's flow, not by changing any fundamental laws of physics, but by exploiting the natural variation in time's passage under different physical conditions. However, the time dilation achievable with current or near-future technology remains modest from a human perspective. Even aboard the International Space Station, where astronauts orbit at approximately 28,000 kilometers per hour, the time dilation amounts to only about 0.01 seconds over a 6-month mission. After spending a total of 879 days in space across multiple missions, former cosmonaut Gennady Padalka experienced a time shift of just 1/44 of a second compared to Earth. To achieve more dramatic time dilation effects, the kind that might allow humans to effectively travel years into the future, we would need to reach velocities far beyond current capabilities or harness gravitational fields of extraordinary intensity. Both approaches present enormous technological challenges. Accelerating a spacecraft to, say, 99% of light speed would require energy equivalent to the annual electricity production of the entire United States, even for a relatively small vehicle. Conventional rocket propulsion is wholly inadequate for the task. More exotic propulsion methods, nuclear pulse propulsion, antimatter engines, or massive external accelerators remain speculative or in early stages of theoretical development. Similarly, creating or harnessing gravitational fields intense enough for significant time dilation would require manipulating masses on the scale of stars or planets, an engineering challenge far beyond our current capabilities. While naturally occurring objects like black holes create such conditions, approaching them closely enough to experience dramatic time dilation would expose travelers to lethal radiation and gravitational forces. Yet the theoretical possibility remains tantalizing. If humanity could someday overcome these technological barriers, perhaps through breakthroughs in fusion power, antimatter production, or gravity manipulation, we might eventually achieve time dilation significant enough to serve as a form of time travel to the future. Imagine a spacecraft accelerated to 99.995% of light speed. For each year experienced by the crew, a century would pass on Earth. A 5-year mission, from the crew's perspective, would return to an Earth 500 years in the future. The astronauts would have effectively skipped half a millennium, becoming time travelers in a very real sense. Such capabilities would raise profound questions about human society and identity. Would people volunteer for missions knowing they could never return to the world they knew? How would society reintegrate travelers from the distant past? Would time-dilated travel become a one-way journey to witness the far future, a form of extreme tourism for the adventurous? These questions remain speculative for now, but they highlight an important point. Even without exotic physics like wormholes or tachyons, Einstein's well-established theories provide a pathway to limited forms of time travel. The future, at least, appears to be accessible through sufficiently advanced technology. But what about travel to the past? Here, the picture becomes much more complicated. While the same relativistic physics that permits future travel through time dilation doesn't explicitly forbid past travel, it provides no obvious natural mechanism for it. To contemplate journeys into the past, we must venture beyond the relatively straightforward physics of time dilation into more speculative realms involving extreme distortions of space-time. Before we explore these more exotic possibilities, let's consider the significance of what we already know with certainty. Time is not the rigid, universal flow that our everyday experience suggests. It stretches and compresses depending on motion and gravity. It passes at different rates for different observers. And under the right conditions that are extreme but not theoretically impossible, these variations can become dramatic enough to constitute a form of time travel. This realization represents a profound shift in our understanding of reality. Time, once thought immutable and absolute, has been revealed as plastic and relative. The temporal barriers that seem to confine us to the present moment may not be as impenetrable as they appear. As we've seen, subatomic particles routinely experience significant time dilation, effectively traveling into the future relative to their surroundings. The same principles apply to larger objects, including humans, though the technological challenges of achieving relativistic speeds or generating extreme gravitational fields currently place practical limits on the magnitude of the effect. These limits may not be permanent. Throughout history, technological barriers that once seemed insurmountable have eventually yielded to human ingenuity and determination. The sound barrier, once thought potentially impossible to breach, fell to the X-1 aircraft in 1947. The challenge of spaceflight, deemed fantastical for centuries, was overcome just decades after the Wright brothers' first flight. Perhaps someday, the barriers to significant time dilation will likewise be overcome. Future generations might harness fusion power or antimatter to accelerate spacecraft to significant fractions of light speed. They might develop technologies to generate or manipulate gravitational fields of sufficient intensity to create noticeable temporal effects. They might even discover new physical principles that provide alternative pathways to temporal manipulation. For now, time dilation remains primarily an object of scientific study rather than practical application, with the notable exception of precision timekeeping systems like GPS. Yet its existence proves something crucial. Time travel, at least in the limited sense of journeying to the future, is not merely science fiction. It's a natural consequence of physical laws we have already verified experimentally. This realization opens the door to more speculative inquiries. If one form of time travel is possible in principle, might others be possible as well? If time can be stretched by motion and gravity, could it also be bent back upon itself under sufficiently extreme conditions? To explore these possibilities, we must venture beyond the realm of time dilation into environments where space-time becomes even more drastically distorted. Environments like black holes, where the conventional rules of physics approach their breaking point. As we transition to our exploration of these more exotic possibilities, we carry with us a crucial insight. The manipulation of time through dilation effects is not a violation of physical law, but an expression of it. Time travel, at least in this limited form, doesn't require breaking the rules of physics. It merely requires exploiting them under extreme conditions. The twin who returns from a near light-speed journey, measurably younger than their Earthbound sibling, has not violated any physical principle. They have simply followed a different path through space-time, a path where time, for them, passed more slowly relative to Earth. They have become, in a very real sense, a traveler from the past who has jumped ahead to witness a future that, for Earthbound observers, unfolded gradually over many years. This perspective reveals something profound about the nature of time and our place within it. We are all, in a sense, travelers through the fourth dimension, moving inexorably forward at rates determined by our motion and gravitational environment. The fact that these rates can vary, that time itself is relative rather than absolute, hints at possibilities that transcend our everyday experience of temporal reality. As we prepare to explore more exotic temporal phenomena, we should acknowledge the significance of what we already know with certainty. Time is malleable. Its flow can be altered by motion and gravity, and in this malleability may lie the key to temporal journeys far more dramatic than the subtle effects we've observed thus far. Journeys that might someday allow humans to witness futures distant beyond imagining, or perhaps even to revisit a past long thought irretrievably lost to time's relentless forward march. Having explored how motion and gravity can stretch and compress time through dilation effects, we now venture into more exotic territory, regions of space where gravity becomes so intense that the fabric of space-time warps dramatically, potentially creating conditions conducive to more radical forms of time travel. These cosmic phenomena, black holes and their theoretical cousins, wormholes, represent nature's most extreme laboratories for testing the limits of Einstein's theories and perhaps discovering pathways through time itself. Black holes have transitioned from theoretical curiosities to observationally confirmed objects over the past century. These gravitational behemoths form when massive stars exhaust their nuclear fuel and collapse inward, compressing an enormous amount of mass into an infinitesimally small volume. The result is an object so dense that its gravitational pull prevents even light from escaping beyond a boundary known as the event horizon. The existence of black holes was first predicted mathematically through Einstein's general theory of relativity. In 1916, just months after Einstein published his groundbreaking theory, the German physicist Karl Schwarzschild discovered a solution to Einstein's field equations that described the space-time around a perfectly spherical mass. When this mass is sufficiently compressed, Schwarzschild's solution reveals a singularity, a point where space-time curvature becomes infinite, and the known laws of physics break down. For decades, many physicists, including Einstein himself, considered black holes to be mathematical artifacts rather than real astronomical objects. The idea that matter could collapse to infinite density seemed too bizarre to be physically plausible. However, in the 1960s and 1970s, observational evidence began to mount. The discovery of quasars, incredibly bright objects powered by matter, falling into supermassive black holes, and the detection of X-ray emissions from binary star systems, where one member appeared to be a black hole, gradually convinced the scientific community of their existence. In recent years, the evidence has become overwhelming. In 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole's shadow, a dark silhouette against the bright background of hot gas orbiting the supermassive black hole at the center of Galaxy M87. In 2020, the Nobel Prize in Physics was awarded to Roger Penrose, Reinhard Genzel, and Andrea Ghez for their theoretical and observational work on black holes. And gravitational wave observatories have detected the ripples in spacetime created when black holes collide and merge. These observations have confirmed what Einstein's equations predicted. Black holes create the most extreme distortions of spacetime known to exist in our universe. And these distortions have profound implications for the flow of time. Near a black hole, time dilation reaches extraordinary levels. As an object approaches the event horizon, time passes more and more slowly from the perspective of a distant observer. An astronaut falling toward a black hole would appear to move in increasingly slow motion, eventually seeming to freeze in time at the horizon itself. From the astronauts' perspective, however, time would continue to pass normally. They would cross the event horizon without noticing any dramatic change in their experience of time's passage. This asymmetry highlights one of the most counterintuitive aspects of time near black holes. The relativity of simultaneity becomes stretched to its limit. Events that appear to occur at vastly different times from a distant observer's perspective might happen almost simultaneously from the falling astronaut's viewpoint. Conversely, what seems like a brief moment to the distant observer might correspond to eons for the astronaut. This extreme time dilation makes black holes natural time machines in a limited sense. An astronaut who orbited very close to a black hole's event horizon for what subjectively felt like days or weeks might return to find that years or centuries had passed on Earth. Like the twin traveling at near-light speed, they would have effectively journeyed into the future. But black holes offer another, more exotic possibility for time manipulation through what physicist Kip Thorne calls time-like curves. In certain types of black holes, particularly rotating ones known as Kerr black holes, Einstein's equations suggest the possibility of paths through space-time that loop back upon themselves temporally, potentially allowing travel into the past. Discovered mathematically by Roy Kerr in 1963, rotating black holes have additional properties beyond those of static black holes. Their rotation drags the fabric of space-time around them in a process called frame dragging, creating a region called the ergosphere, where objects are forced to rotate with the black hole. More importantly for our discussion, rotating black holes might contain ring-shaped singularities rather than point singularities, opening the theoretical possibility of traversable paths through their centers. Some solutions to Einstein's equations suggest that under very specific conditions, an object might enter a rotating black hole, pass through its ring singularity without being destroyed, and emerge not just in another location, but at another time, potentially even in the past relative to when it entered. This would constitute a closed time-like curve, a path through space-time that returns to its starting point in time. These mathematical solutions don't necessarily correspond to physical reality. The extreme conditions inside a black hole's event horizon might invoke quantum gravitational effects not accounted for in Einstein's classical theory. The singularity itself represents a breakdown of known physics, a domain where our current theories cannot make reliable predictions. Nevertheless, the fact that such possibilities emerge naturally from our best theory of gravity suggests that nature might permit journeys through time under conditions extreme enough to test the limits of space-time itself. Even more tantalizing than black holes for potential time travel are their theoretical cousins, wormholes. First conceptualized by physicists Albert Einstein and Nathan Rosen in 1935, then called Einstein-Rosen bridges. Wormholes represent hypothetical tunnels through space-time that could connect widely separated regions of the universe, or even different universes within a theoretical multiverse. In their original formulation, Einstein-Rosen bridges were not traversable. They would collapse too quickly for anything to pass through them. However, in 1988, physicist Kip Thorne and his colleagues proposed that a sufficiently advanced civilization might be able to keep a wormhole open by threading it with exotic matter, material with negative energy density that would counteract the wormhole's tendency to collapse. While exotic matter with negative energy density might seem purely speculative, quantum field theory does predict phenomena like the Casimir effect, where quantum fluctuations in vacuum energy can create regions of effectively negative energy density between closely spaced plates. Whether such effects could be harnessed to stabilize a macroscopic wormhole remains highly dubious with current physics, but the theoretical possibility cannot be entirely dismissed. If traversable wormholes could exist, they would offer remarkable possibilities for space travel, potentially allowing journeys across vast cosmic distances without having to traverse the intervening space. But even more intriguingly, they might serve as gateways through time, as well as space. This temporal potential arises because the two mouths of a wormhole could exist in regions of space-time with different gravitational potentials or relative velocities. If one mouth were placed near a black hole or accelerated to relativistic speeds, time would pass at different rates at each end of the wormhole due to the time dilation effects we've already discussed. Consider a hypothetical scenario. One mouth of a wormhole remains stationary on Earth, while the other is placed aboard a spacecraft and accelerated to 99.995% of light speed. After a subjective year of travel for the moving wormhole mouth, it would have aged only 1 year, but the stationary mouth on Earth would have aged 100 years due to relativistic time dilation. At this point, the wormhole would connect 2 points separated not just in space, but in time. An object entering the mouth aboard the spacecraft would exit from the Earthbound mouth 99 years in the future relative to when it entered. Conversely, something entering the Earthbound mouth would emerge 99 years in the past from the perspective of someone at the spacecraft mouth. This setup would effectively create a portal between two different times. A person could step through the wormhole and meet their younger or older self, depending on which direction they traveled. Information could be sent backward in time, potentially altering the sequence of causes and effects that led to the wormhole's creation in the first place. Such capabilities would raise the specter of paradoxes, logical contradictions that seem to forbid certain types of time travel. The most famous is the grandfather paradox. If you traveled to the past and prevented your grandfather from meeting your grandmother, you would never have been born. In which case, how could you have traveled back in time to prevent the meeting? This apparent logical impossibility has led many physicists to suggest that nature must forbid travel to the past, even if the mathematics of relativity seems to permit it. However, various theoretical resolutions to these paradoxes have been proposed. Perhaps the most intriguing is the Novikov self-consistency principle, formulated by Russian physicist Igor Novikov. This principle suggests that time travel might be possible, but only in ways that avoid paradoxes. Events on closed time-like curves must be self-consistent, forming closed loops of causality without logical contradictions. In the context of the grandfather paradox, the Novikov principle would assert that something would always prevent the time traveler from killing their grandfather. Perhaps they would slip on a banana peel, their weapon would jam, or they would have a sudden change of heart. The universe would conspire to preserve causal consistency. Another potential resolution comes from quantum mechanics in the form of the many worlds interpretation. According to this view, when a time traveler changes the past, they don't alter their own timeline, but instead create a new branch of reality, a parallel universe where events unfold differently. The time traveler would have come from a timeline where their grandfather lived to produce their parent, but their actions would create a new timeline where their grandfather died before reproduction. No logical contradiction would arise because the two versions of history would exist in separate branches of a multiversal reality. These resolutions remain speculative, but they suggest that time travel to the past might not be logically impossible after all. The laws of physics as we currently understand them don't definitively prohibit such journeys, even if they would require conditions and technologies far beyond our current capabilities. It's worth noting that both black holes and wormholes as time machines would present enormous practical challenges, even if the underlying physics permits their use. Black holes are extraordinarily dangerous environments with lethal radiation, intense tidal forces that would stretch any physical object into a process whimsically termed spaghettification, and extreme gravitational fields that would crush matter at the atomic level. Any civilization hoping to use black holes for time manipulation would need technologies far beyond our current understanding to protect travelers from these lethal conditions. Wormholes, meanwhile, remain entirely theoretical. No wormhole has ever been observed, and creating one would likely require energies and exotic matter beyond anything we can currently produce or manipulate. Keeping a wormhole stable enough for traversal would be an even greater challenge, requiring precise control of negative energy densities that may not be physically possible in the quantities needed. Nevertheless, The theoretical possibility of using these extreme space-time geometries for time travel continues to fascinate physicists. In 1991, Stephen Hawking proposed what he called the chronology protection conjecture, suggesting that the laws of physics somehow forbid closed time-like curves and thus prevent travel to the past. Hawking argued that quantum effects would likely destabilize any incipient time machine, preventing paradoxes from arising in the first place. Yet no definitive physical law has been identified that would absolutely prohibit time travel under all circumstances. The tension between general relativity, which seems to permit closed time-like curves under certain conditions, and quantum mechanics, which might forbid them through back-reaction effects, highlights one of the great unresolved issues in theoretical physics: the need for a quantum theory of gravity that can make reliable predictions about space-time behavior in extreme environments. Some approaches to quantum gravity, such as loop quantum gravity and certain formulations of string theory, suggest that space-time itself might have a granular structure at the Planck scale, approximately 10 to the power of negative 35 meters. If true, this quantization might impose fundamental limits on how sharply space-time can curve, potentially preventing the formation of the closed time-like curves necessary for past-directed time travel. Others argue that even if the underlying physics permits time travel, the practical requirements would be so extreme that it might remain forever beyond the reach of even the most advanced civilizations. Creating a traversable wormhole might require energy equivalent to the mass of Jupiter, converted entirely to energy, manipulated with precision on subatomic scales. Stabilizing such a wormhole against quantum fluctuations might be even more demanding. Yet the history of science cautions against declaring anything absolutely impossible. Technologies that would have seemed magical to our ancestors, from global video communication to nuclear energy to space travel, have become commonplace through advances in our understanding of physical law and our ability to manipulate matter and energy. Perhaps, someday, a civilization with a deeper understanding of quantum gravity and access to energies and materials we can barely imagine might indeed harness black holes or wormholes for journeys through time. For now, these exotic possibilities remain largely in the realm of theoretical physics and science fiction, but they remind us how far our understanding of time has evolved, from Newton's absolute universal flow to Einstein's flexible dimension of space-time, to the modern recognition that under extreme enough conditions, time might loop back upon itself or fork into multiple realities. The study of black holes and wormholes represents the frontier of this evolving understanding, the domain where our best theories approach their limits and hint at possibilities beyond our current comprehension. By exploring these extreme regions mathematically and increasingly observationally, physicists hope to gain insights not just into the possibility of time travel, but into the fundamental nature of space-time itself. As we continue our journey through the physics of time travel, we must confront the logical puzzles and paradoxes that arise when we contemplate journeys to the past. For while the mathematics of relativity may permit such journeys under certain conditions, they raise profound questions about causality and free will, questions that touch on the very foundations of reality as we understand it. The extreme time dilation near black holes and the potential temporal connections through wormholes offer tantalizing possibilities for temporal manipulation, but they also challenge our intuitive understanding of cause and effect, of choices and their consequences, of time's seemingly inexorable forward flow. To fully assess the possibility of time travel, we must grapple not just with the physics of space-time, but with the logical implications of altering the past or foreseeing the future. In our exploration of black holes and wormholes as potential time machines, we've ventured to the frontiers of known physics, examining solutions to Einstein's equations that suggest pathways through time as well as space. While current technology and energy resources place practical limitations on our ability to exploit these pathways, the theoretical possibility remains intriguing. Black holes, with their extreme gravitational fields and distortions of space-time, create conditions where time dilation reaches its maximum possible extent. An observer hovering near a black hole's event horizon would witness the future of the distant universe unfolding at an accelerated rate, while for distant observers, the passage of time for anything near the black hole would appear to slow dramatically, eventually freezing at the horizon itself. Rotating black holes might offer even more exotic possibilities through their complex internal geometry, potentially allowing traversable paths that lead not just to other regions of space, but to other times as well. While the extreme conditions near the singularity present major theoretical and practical challenges to using black holes as time machines, they remain one of the few natural phenomena that might permit temporal manipulation beyond simple time dilation. Wormholes, meanwhile, represent an even more speculative but potentially more controllable approach to time travel. By connecting regions of space-time with different temporal coordinates, perhaps through differential aging of the wormhole mouths via relativistic time dilation, they could theoretically create traversable shortcuts through time as well as space. Both approaches would require technologies and energy sources far beyond our current capabilities, and both raise profound questions about causality and the logical consistency of a universe where effects might precede causes. Yet the fact that such possibilities emerge naturally from our best theory of gravity suggests that time travel cannot be dismissed out of hand as physical impossibility. As we transition to our exploration of time travel paradoxes, we carry with us this crucial insight: the extreme distortions of space-time near black holes and within theoretical wormholes push our understanding of physics to its limits. In these exotic environments, time loses its familiar linear character, becoming as malleable and navigationable as the spatial dimensions through which we move freely in our everyday experience. Whether this malleability can ever be harnessed for practical time travel remains an open question, one that touches on the deepest mysteries of modern physics, from the quest for quantum gravity to the nature of causality itself. But the journey toward an answer continues to yield profound insights into the nature of time and our place within the temporal fabric of the universe. Having explored the physical mechanisms that might potentially enable time travel, we now confront perhaps the most perplexing aspect of temporal journeys: the paradoxes they seem to create. These logical dilemmas have troubled philosophers and physicists alike, suggesting that time travel, particularly to the past, might be forbidden not by the laws of physics, but by the laws of logic. The most famous of these conundrums is the grandfather paradox, a thought experiment that has become a staple of science fiction and serious theoretical discussions alike. In its classic formulation, the paradox asks, what would happen if a time traveler went back in time and killed their own grandfather before their parent was conceived? If the grandfather died before producing the time traveler's parent, then the time traveler would never have been born, in which case they couldn't have traveled back in time to kill their grandfather in the first place. This creates an apparent logical contradiction, a loop of impossibility that seems to suggest time travel to the past must be impossible. If the time traveler succeeds in their grim mission, they erase the very conditions that allowed them to exist and make the journey. If they fail, the reason must be that they already exist, which means their grandfather survived to produce their parent. Either way, the timeline remains consistent, but the time traveler's free will appears compromised by the demands of logical consistency. The grandfather paradox can be generalized to any situation where a time traveler attempts to change the past in a way that would prevent their own time travel journey. For instance, if you traveled back in time to prevent yourself from building a time machine, you would create the same logical contradiction. If you succeed, you eliminate the means by which you traveled back, making your intervention impossible. This paradox strikes at the heart of our understanding of causality, the principle that causes precede their effects in a clear temporal sequence. Time travel to the past seems to permit effects, the time traveler's actions, to precede their causes, the events that led to the time traveler's existence, creating circular causation that defies our intuitive understanding of how reality operates. Several potential resolutions to the grandfather paradox have been proposed, each with profound implications for our understanding of time, free will, and the nature of reality itself. The first resolution is the Novikov self-consistency principle, proposed by Russian physicist Igor Novikov in the 1980s. According to this principle, time travel might be possible, but only in ways that avoid paradoxes. The universe, in effect, conspires to prevent logical contradictions. If you try to kill your grandfather, something will always stop you. Your gun will jam, you'll slip on a banana peel, or you'll have a last-minute change of heart. Not because of some mystical force protecting the timeline, but because the only consistent solutions to the equations governing reality are those where no paradoxes occur. In the mathematics of general relativity, this corresponds to accepting only those solutions to Einstein's field equations that don't produce inconsistencies. Time travel might be permitted, but only along world lines that create closed, self-consistent loops in space-time without logical contradictions. The Novikov principle preserves both time travel and causality, but at a potential cost to free will. Time travelers wouldn't be able to change events they know happened, no matter how hard they tried. Their apparent choices would be constrained by the requirement for consistency. Some find this limitation philosophically troubling, as it suggests a kind of predestination for time travelers. Their future actions in the past are already fixed and unmalleable. A second resolution comes from quantum mechanics in the form of the many worlds interpretation. Proposed by Hugh Everett III in 1957, this interpretation suggests that every time a quantum system faces multiple possible outcomes, reality branches into parallel universes, each containing one of the possible results. Applied to time travel, the many worlds interpretation suggests that when a time traveler goes back and changes the past, they aren't changing their own past, but creating a new timeline, a parallel reality where events unfold differently. The time traveler would come from a timeline where their grandfather lived to reproduce, but their intervention would create a new branch of reality where their grandfather died before reproduction. In this view, no paradox occurs because there are two distinct timelines. The original one, where the time traveler was born normally and eventually traveled back in time, and the new one, where the grandfather died prematurely and the time traveler was never born in that timeline. The time traveler doesn't disappear upon killing their grandfather because they remain a visitor from the original timeline, now stranded in a divergent reality they've created through their intervention. This resolution preserves free will. Time travelers can make whatever changes they want, but at the cost of abandoning the idea of a single unified timeline. Reality becomes a branching tree of possibilities rather than a linear progression, with time travel creating new branches rather than altering the main trunk. A third resolution, more exotic than the previous two, involves what philosophers call a causal loop, or physicists call a closed time-like curve. In this view, certain events might have no clear origin, but exist in a self-supporting temporal loop. Consider a variation of the grandfather paradox. Instead of killing your grandfather, you travel back in time, and through a series of events, end up becoming your own grandfather. Your existence is then part of a closed loop. You exist because you went back in time to ensure your own birth. While bizarre, such loops don't contain logical contradictions. They're strange, but internally consistent. Similarly, information or objects might exist in causal loops without clear origin. Imagine finding the plans for a time machine, using them to build the device, then traveling back to give your younger self the same plans. Where did the plans originally come from? They exist in a loop with no clear beginning or end. This phenomenon, called the bootstrap paradox, named after the impossible feat of pulling oneself up by one's bootstraps, doesn't create logical contradictions, but does challenge our understanding of causation. Information or objects in such loops appear to have no clear origin. They simply exist as self-perpetuating temporal artifacts. Physicists like J. Richard Gott and Li-Hsin Li have shown that closed time-like curves can be consistent with Einstein's equations under certain conditions. While they seem bizarre from our everyday perspective, they don't violate any known laws of physics. They merely require us to abandon our intuitive understanding of linear causality. A fourth resolution, less satisfying to many theorists but worth considering, is that time travel to the past might simply be physically impossible, despite the apparent allowances in Einstein's equations. Stephen Hawking proposed the chronology protection conjecture, suggesting that the laws of physics somehow forbid closed time-like curves, making time travel to the past impossible and thus preventing paradoxes from arising in the first place. Hawking argued that quantum effects would generate catastrophic vacuum fluctuations at the moment a time machine was activated, destroying the device before it could create a closed time-like curve. While no definitive proof of this conjecture has been found, it represents an attempt to reconcile the apparent mathematical possibility of time travel with the logical problems it raises. Beyond the grandfather paradox, time travel raises other perplexing dilemmas. One is the predestination paradox, where attempts to prevent a future event through time travel actually cause that very event. In this scenario, causality remains intact, but in a circular fashion that challenges our understanding of free will and determination. For example, imagine learning that a laboratory accident will occur next week. You travel back in time to prevent it, but in your attempts to disable the equipment, you inadvertently cause the very accident you were trying to prevent. Your intervention doesn't change history, it fulfills it, creating a closed loop where effect becomes cause and cause becomes effect. Unlike the grandfather paradox, the predestination paradox doesn't create logical contradictions. It's strange but consistent. History unfolds as it always already did, with the time traveler's interventions being part of that history all along. But this consistency comes at the cost of apparent free will. The time traveler can't change events, only fulfill their predestined role in them. This leads to another dilemma, the knowledge paradox. If you travel to the future, learn something, like lottery numbers or scientific discoveries, then return to use that knowledge. Where did the information originally come from? Not from traditional research or chance. It emerges from a loop between future and past with no clear point of origin. Similarly, imagine traveling to the future, reading a book that hasn't been written yet, returning to the present, and publishing that same book under your name. Who actually created the content? The information exists in a loop with no original author, a bootstrap paradox applied to knowledge rather than physical objects. These knowledge paradoxes don't necessarily create logical impossibilities, but they challenge our understanding of creativity, discovery, and intellectual development. If information can exist in temporal loops without clear origin, what does this imply about the nature of knowledge itself? Time travel also raises questions about determinism and free will that go beyond specific paradoxes. If the past and future coexist in a four-dimensional block universe, as some interpretations of relativity suggest, and time travel is possible, does this mean all events are fixed and unchangeable? If a time traveler from 2050 visits 2020, does this mean 2050 already exists in some sense, with all intervening events predetermined? In such a universe, apparent choice might be an illusion, a perspective effect arising from our limited three-dimensional perception of a fully determined four-dimensional reality. Time travelers would be like readers jumping between different pages of an already written book, able to move non-sequentially through the story, but unable to change its content. Alternatively, if reality is more like a choose-your-own-adventure book with multiple possible pathways, time travel might allow navigation between different possible timelines. This view aligns more closely with the many worlds interpretation, suggesting that the future isn't fixed, but consists of multiple possibilities, some of which might be accessed through temporal journeys. These philosophical questions become even more complex when we consider the social and ethical implications of time travel. If time travel to the past were possible, would we have a moral obligation to prevent historical atrocities? What about the butterfly effect? The idea that small changes in the past might have enormously magnified consequences in the future, potentially erasing billions of lives and creating billions of different ones. Science fiction has explored these dilemmas extensively, often concluding that the wisdom of the prime directive, non-interference with the past, might be the only ethically defensible position. But this non-interference would severely limit the utility of time travel, reducing it to an observational tool rather than a means of actively changing events. Perhaps the most profound implication of time travel paradoxes is what they reveal about the nature of time itself. If time travel is logically possible, even if practically challenging, then time cannot be the simple linear flow we intuitively experience. It must be something more complex, perhaps a dimension as navigable as space, perhaps a branching tree of possibilities, perhaps a closed loop where future and past influence each other in a cosmic dance of causality. Some theoretical physicists, including Julian Barber, have gone so far as to suggest that time as a flowing entity doesn't exist at all, that what we perceive as the passage of time is an illusion arising from the relationship between different states of the universe. In Barber's view, each moment exists as a complete now, what he calls a time capsule, containing records of other nows that we interpret as past events. This perspective aligns with what physicists call the block universe, or eternalism, the view that past, present, and future all exist simultaneously in a four-dimensional space-time block. From this perspective, time travel paradoxes might arise from our misunderstanding of time's fundamental nature. If all moments exist eternally, then traveling between them doesn't change the block. It merely allows navigation through an already existing structure. Other theorists, like Lee Smolin, argue for a different view: presentism, the idea that only the present moment truly exists, with the past gone and the future not yet formed. In this perspective, time travel to the past would be impossible not because of logical paradoxes, but because the past no longer exists as a destination. However, this view struggles to reconcile with the relativistic picture of space-time as a unified four-dimensional manifold. Between these extremes lies a range of intermediate positions, each with different implications for the possibility and consequences of time travel. Growing block theory, for instance, suggests that the past and present exist, but the future does not, which would permit travel to the past but not the future. Branching space-time theories allow for multiple possible futures, but a single past, until time travelers intervene to create new branches. The key insight from these philosophical explorations is that time travel paradoxes aren't merely puzzles about the mechanics of hypothetical time machines. They're windows into the fundamental nature of time, causality, and reality itself. By contemplating what would happen if we could move freely through time, we gain insights into what time actually is. And these insights sometimes challenge our most basic intuitions about how the universe works. From a practical perspective, the paradoxes associated with time travel, particularly to the past, represent significant theoretical obstacles that any viable time travel mechanism would need to address. Whether through Novikov-style self-consistency, many worlds branching, closed causal loops, or some other resolution, the logical contradictions must be resolved before we can consider time travel a serious possibility rather than merely an intriguing thought experiment. For many physicists, these paradoxes strengthen the case for Hawking's chronology protection conjecture, the idea that the laws of physics somehow forbid closed time-like curves and travel to the past. Yet the fact that such paradoxes arise from our best physical theories suggests something profound. Either time travel to the past is indeed impossible, or our understanding of time, causality, and reality itself requires fundamental revision. As we continue our exploration of cosmic time travel, we'll examine more speculative physical mechanisms that might potentially enable temporal journeys, from cosmic strings to rotating cylinders of exotic matter. But we'll carry with us the insights from these paradoxes, recognizing that the logical challenges of time travel may prove as formidable as the physical ones. Perhaps someday, a unified theory of quantum gravity will resolve these dilemmas, revealing whether closed time-like curves can exist in a physically and logically consistent universe. Until then, the paradoxes of time travel remain both a theoretical obstacle and an intellectual opportunity. a chance to probe the deepest mysteries of temporal reality through the lens of hypothetical journeys through time. The most profound implication of these paradoxes may be what they reveal about our place in the cosmos. As beings who experience time linearly, moving inexorably from past to future at a fixed rate, we struggle to conceptualize temporal loops, branching timelines, or block universes where all moments exist simultaneously. Our intuitive understanding of cause and effect, of choice and consequence, assumes a unidirectional flow of time that these paradoxes challenge. Perhaps the ultimate resolution to time travel paradoxes lies not in the physics of wormholes or the mathematics of closed time-like curves, but in a fundamental reconceptualization of time itself. A shift in perspective as profound as the Copernican revolution that removed Earth from the center of the cosmos. Just as we came to understand that our planet's apparent centrality was an illusion born of our limited perspective, perhaps the apparent impossibility of paradox-free time travel reflects our limited temporal perspective rather than an absolute prohibition in the laws of physics. As we transition to exploring more speculative mechanisms for time travel, we should remember that the paradoxes we've examined aren't merely logical puzzles, but profound questions about the nature of reality. They remind us that time, the dimension we navigate every moment of our lives, remains in many ways more mysterious than the vast spatial expanses of our universe. While the grandfather paradox and its variants present significant conceptual challenges to the possibility of time travel, they don't definitively prove its impossibility. Rather, they suggest that if such journeys are possible, reality must work in ways that differ dramatically from our intuitive understanding, perhaps through self-consistent loops, branching timelines, or other frameworks that can accommodate apparent violations of linear causality without creating true logical contradictions. The search for these frameworks continues at the frontiers of theoretical physics, where speculative mechanisms for time travel point toward possibilities as strange and wondrous as the paradoxes they might create. And it is to these mechanisms, cosmic strings, Tipler cylinders, and other exotic configurations of matter and energy that we now turn our attention. Having explored the logical paradoxes that challenge the possibility of time travel, we now turn to some of the most speculative yet mathematically consistent mechanisms that might potentially enable temporal journeys. These theoretical constructs, from cosmic strings to rotating cylinders of dense matter, emerge from solutions to Einstein's field equations that permit closed time-like curves, potentially allowing travelers to journey into their own past. Unlike the relatively straightforward time dilation effects we discussed earlier, which have been experimentally verified and merely allow one-way travel to the future, these more exotic possibilities remain purely theoretical. None has been observed in nature or created in a laboratory, yet they represent serious scientific speculations based on our best understanding of how space-time behaves under extreme conditions. Let's begin with cosmic strings, perhaps the most exotic of these theoretical possibilities. First proposed in the 1970s as part of grand unified theories in particle physics, cosmic strings are hypothetical one-dimensional defects in spacetime that may have formed during phase transitions in the early universe, similar to how cracks form in ice as water freezes. These are not ordinary strings like those we encounter in everyday life, but incredibly thin, extremely dense filaments that may stretch across vast cosmic distances. A cosmic string just 1 kilometer long might contain as much mass as Earth. Their extraordinary density would create powerful gravitational effects, distorting the space-time around them in unique ways. What makes cosmic strings particularly interesting for potential time travel is their gravitational properties. Unlike normal massive objects that attract matter from all directions, cosmic strings would create a distinctive gravitational field without attracting objects toward them. Instead, space around a cosmic string would be flat, but with a missing wedge, as if you cut a slice from a pizza and then push the remaining pieces together. This creates what physicists call a conical singularity. In 1991, Physicist J. Richard Gott published a paper in Physical Review Letters describing how two cosmic strings moving past each other at high speeds could, in theory, create closed time-like curves, paths through space-time that return to their starting point in time as well as space. An advanced civilization might potentially use such an arrangement as a time machine, allowing travel into the past. The physics behind this possibility is complex, involving what happens when the missing wedges of space-time around two rapidly moving cosmic strings overlap. Under very specific conditions, Gott showed mathematically that this configuration would allow objects to travel along paths that arrive back at their starting point in time before they departed, effectively traveling to the past. Importantly, Gott's solution doesn't require exotic matter with negative energy or mass, just the cosmic strings themselves, which are at least theoretically possible according to some extensions of the standard model of particle physics. This makes cosmic string time machines somewhat less speculative than wormhole-based approaches, which typically require material with properties that may violate energy conditions in general relativity. However, subsequent analysis by Hawking and others suggested that creating a time machine using Gott's cosmic string method would require strings of infinite length or energy equivalents that exceed the total mass energy of the observable universe, rendering it practically impossible even for a hyper-advanced civilization. Furthermore, cosmic strings themselves remain hypothetical. Despite searches using gravitational wave detectors, cosmic microwave background observations, and gravitational lensing surveys, no definitive evidence for their existence has been found. While they haven't been ruled out, the lack of observational confirmation places cosmic string time machines firmly in the realm of interesting but unverified theoretical possibilities. Another speculative approach to time travel involves what's known as a Tipler cylinder, named after physicist Frank Tipler, who described it in 1974. This concept involves a massive, infinitely long cylinder rotating at speeds close to that of light. The rotation of such an enormous mass would drag space-time around with it, an effect called frame dragging that has been experimentally verified on a much smaller scale by measurements of Earth's rotation. In the case of a Tipler cylinder, the frame dragging would be so extreme that space-time would twist into closed time-like curves, potentially allowing travel into the past. An advanced civilization might, in theory, construct such a cylinder or find a naturally occurring object with similar properties, like a rapidly rotating neutron star or black hole, and use the resulting space-time distortions for time travel. Like the cosmic string approach, Tipler cylinders don't require exotic matter with negative energy density. However, they do require either an infinitely long cylinder or, in modified versions, extreme mass and rotational speeds that may not be physically achievable. Additionally, the tidal gravitational forces near such objects would likely be lethal unless the time traveler had access to equally advanced protective technology. A third approach, proposed by physicist Kip Thorne and his colleagues, involves what's called the Orisoan spacetime. This is a variation on wormhole-based time machines that attempts to address some of the issues with traditional traversable wormholes, particularly their requirement for exotic matter with negative energy density. The Orisoan model uses a special arrangement of matter in a toroidal, donut shape, combined with a spherical shell of ordinary matter. Under specific conditions, this configuration could theoretically create a region of space-time where closed time-like curves exist, potentially allowing for time travel without the need for exotic matter with negative energy density. While this approach reduces some of the physical requirements that make other time machine designs seem impossible, it still faces significant challenges. The precise arrangement of matter required would be extraordinarily difficult to create, and quantum effects might still destabilize the time machine, as suggested by Hawking's chronology protection conjecture. Another intriguing possibility comes from theoretical work on rotating black holes. As we discussed earlier, black holes represent regions where space-time is maximally distorted by extreme mass concentration. When a black hole rotates, it drags space-time around with it, creating a region called the ergosphere, where nothing can remain stationary relative to distant stars. everything must rotate with the black hole. Kerr black holes. Rotating black holes named after mathematician Roy Kerr, who found the solution to Einstein's equations describing them, have additional properties beyond those of static black holes. Their rotation creates a ring-shaped singularity rather than a point singularity, and under certain theoretical conditions, this might allow for a path through the black hole that avoids crushing gravitational forces and emerges elsewhere and elsewhen. Physicist Roy Kerr discovered this solution to Einstein's field equations in 1963, revealing that a rotating black hole might potentially serve as a portal, not just to other regions of space, but to other times as well. The mathematics suggest that an object entering a Kerr black hole along a specific trajectory could emerge in the past or future relative to when it entered. Of course, enormous practical challenges would make this approach to time travel extraordinarily difficult, even for a far advanced civilization. The radiation, tidal forces, and other extreme conditions near a black hole would destroy any conventional spacecraft or biological entity. The precise control required to navigate through the narrow safe path, if it exists, would be beyond current technological capabilities by many orders of magnitude. Additionally, recent work in quantum gravity suggests that the interior structure of black holes may be more complex than indicated by classical general relativity alone. Quantum effects might eliminate the passable routes through rotating black holes that appear in the classical solutions, closing this potential avenue for time travel. In recent years, theoretical physicists have explored even more exotic possibilities. One involves what's called the Casimir effect, a quantum phenomenon where two uncharged metallic plates placed very close together in a vacuum experience a small attractive force due to quantum fluctuations in the vacuum energy between them. In theory, this effect creates a small region of negative energy density between the plates. Some speculative models suggest that with sufficiently advanced technology, this effect could be magnified and engineered to create the exotic matter needed to stabilize a traversable wormhole or other time machine design. Another approach involves ADS-CFT correspondence, a concept from string theory that suggests a deep connection between gravity in a space with negative curvature, anti-de Sitter or ADS space, and a quantum field theory without gravity on the boundary of that space. Some theoretical work suggests that this correspondence might allow for effective closed time-like curves without actually violating causality in the fundamental theory. These approaches remain at the frontier of theoretical physics, combining aspects of general relativity, quantum field theory, and speculative extensions like string theory. While they provide mathematical frameworks where time travel might be possible, they all face similar challenges: enormous energy requirements, the need for materials or conditions that may be physically impossible, and potential conflicts with quantum effects that might enforce Hawking's chronology protection conjecture. It's worth noting that all these speculative time machine designs share certain features that distinguish them from the familiar time machines of science fiction. None involves a simple device that can be activated to send objects or information to arbitrary points in the past or future. Instead, they all require massive engineering projects involving extreme conditions of matter, energy, and space-time curvature. They also all involve creating specific geometries of space-time where closed time-like curves naturally emerge, paths that loop back to their starting points in time as well as space. A time traveler would need to follow these predefined paths, limiting when and where they could travel. This is quite different from fictional time machines that can target any moment in history with precision. Moreover, many of these theoretical designs would only allow travel back to the point when the time machine was created. You couldn't use them to visit the ancient past or witness the Big Bang. This limitation arises because the closed time-like curves only exist within the specifically engineered region of space-time, not throughout the universe's history. Finally, all these approaches would require energy resources and engineering capabilities far beyond current technology, perhaps beyond what any civilization could ever achieve, no matter how advanced. the energy required often approaches or exceeds the mass energy of entire stars or even galaxies, and the precision required would be at scales where quantum effects become significant, potentially disrupting the very space-time engineering the time machine relies upon. So where does this leave the scientific possibility of time travel? While it might be tempting to dismiss these speculative mechanisms as merely theoretical curiosities, their existence within the mathematics of our best physical theories tells us something important. Time travel to the past is not obviously impossible according to known physics. Unlike concepts that clearly violate fundamental physical laws, such as perpetual motion machines that violate thermodynamics, time travel emerges as a possibility, albeit an extremely challenging one, from legitimate solutions to Einstein's field equations. The fact that serious physicists continue to explore these possibilities suggests that the question remains open from a theoretical perspective. However, the enormous practical challenges, combined with the logical paradoxes we explored earlier, and the potential quantum limitations suggested by Hawking's chronology protection conjecture, make it unlikely that human beings will ever construct a working time machine capable of sending matter or information into the past. As physicist Kip Thorne, one of the most prominent researchers in this field, has noted, the question of whether time travel to the past is possible remains open, but the smart money would bet against it. The combination of physical, practical, and logical obstacles appears formidable, even if no single principle definitively rules it out. Yet the exploration of these theoretical possibilities continues to yield valuable insights into the nature of space-time, the relationship between general relativity and quantum mechanics, and the fundamental structure of reality. By pushing our theories to their limits, asking what happens in the most extreme conditions imaginable, we gain deeper understanding of how the universe works under normal conditions. The study of cosmic strings, for example, connects to fundamental questions in particle physics and cosmology, potentially offering insights into the early universe, regardless of whether they could ever be used for time travel. Similarly, research on rotating black holes and their space-time properties advances our understanding of gravity in extreme environments, with applications to astrophysics and the search for a quantum theory of gravity. In this sense, the scientific exploration of time travel possibilities serves a purpose beyond determining whether such journeys might someday be possible. It functions as a theoretical laboratory for testing the boundaries of our physical theories, revealing potential inconsistencies or unexplored regimes where new physics might emerge. As we continue our journey through the physics of time travel, we'll next consider the practical question: if time machines as described by these theoretical models are so challenging to build, might there be simpler approaches that could at least approximate time travel effects? Could we create technologies that simulate aspects of temporal journeys without requiring cosmic strings or rotating black holes? These questions lead us to consider more modest, but potentially more achievable approaches to manipulating time. Technologies that might not allow true travel to the past, but could enhance our ability to navigate the fourth dimension in more limited ways. The theoretical possibilities we've explored, from cosmic strings to rotating black holes, represent the frontier of scientific speculation about time travel. They emerge from legitimate solutions to Einstein's field equations, suggesting that closed time-like curves and journeys to the past might be mathematically consistent with our best theory of gravity. Yet they all require conditions so extreme, infinite masses, faster than light rotation, exotic matter with negative energy density, that they may remain forever beyond practical realization, even for civilizations far more advanced than our own. And they all potentially face quantum limitations that might enforce causality at the most fundamental level, as suggested by Hawking's chronology protection conjecture. As we transition to considering more practical approaches to time manipulation, we carry with us this key insight: time travel to the past, while not definitively ruled out by known physics, faces obstacles so formidable that it may remain forever in the realm of fascinating theoretical possibilities rather than achievable technology. But travel to the future, through the time dilation effects we explored earlier, faces no such fundamental obstacles. It emerges naturally from well-verified aspects of relativity and requires only sufficiently advanced propulsion technology to achieve velocities where these effects become significant. And it is to these more achievable approaches to time manipulation that we now turn our attention. Having explored the theoretical possibilities for time travel, we now confront the practical question that has tantalized scientists, engineers, and dreamers alike. Could humans actually build a functioning time machine? Is time travel destined to remain a fascinating theoretical curiosity? Or might it someday transition into applied technology? To answer this question, we must distinguish between what's theoretically permitted by the laws of physics and what's practically achievable given the constraints of engineering, energy resources, and the fundamental structure of the universe. As we'll see, the gap between theoretical possibility and practical realization is vast when it comes to time travel technology. Let's begin by considering what would be required to build the various time machines we've discussed in previous sections. For each approach, we'll examine the engineering challenges, energy requirements, and fundamental limitations that would confront any civilization attempting to construct such devices. Traversable wormholes represent one of the most thoroughly explored theoretical approaches to time travel. As we've discussed, a wormhole is essentially a tunnel through space-time that could potentially connect distant regions of space and, if manipulated properly, different points in time as well. To function as a time machine, one mouth of the wormhole would need to be accelerated to relativistic speeds or placed in a strong gravitational field, creating a time differential between the two ends. The engineering challenges of creating such a device are formidable. First, no natural wormholes have ever been observed, so we would need to create one artificially. Current theories suggest this would require manipulating space-time at the quantum level, a feat far beyond current technology. Even if we could somehow nucleate a microscopic wormhole, enlarging it to a size that could accommodate macroscopic objects or human travelers would require extraordinary amounts of energy. Physicists estimate that creating a wormhole just 1 meter in diameter would require energy equivalent to the annual energy output of an advanced civilization harnessing all the power of its parent star, what astronomers call a Type II civilization on the Kardashev scale. Beyond these energy requirements, traversable wormholes appear to require exotic matter with negative energy density to remain stable and open. While quantum field theory does predict small-scale negative energy phenomena like the Casimir effect, it's unclear whether these effects could be amplified sufficiently to stabilize a macroscopic wormhole. Some calculations suggest the amount of negative energy required would exceed what's physically possible, even in principle. Moreover, recent theoretical work suggests that even if a traversable wormhole could be created, it might be fundamentally unstable when used as a time machine. Quantum fluctuations at the wormhole's throat might trigger a runaway feedback loop that would destroy the wormhole precisely when it began to develop closed time-like curves, a specific instance of Hawking's chronology protection conjecture in action. Given these challenges, wormhole-based time machines appear to be, at best, a project for a far future civilization with technology and energy resources vastly exceeding our own, and at worst, fundamentally impossible due to constraints in the laws of physics that we don't yet fully understand. What about cosmic string time machines? As we explored earlier, certain configurations of these hypothetical one-dimensional defects in space-time could theoretically create closed time-like curves, allowing for travel into the past. The challenges here are even more daunting. First, cosmic strings themselves remain hypothetical. None have been definitively detected despite extensive searches. If they do exist, they're likely relics from the early universe, formed during phase transitions as the cosmos cooled after the Big Bang. Creating them artificially would require recreating energy conditions that haven't existed naturally since the first fraction of a second after the universe's birth. Even if naturally occurring cosmic strings exist and could be located, manipulating them would require technology far beyond our current capabilities. Cosmic strings, if they exist, would be incredibly massive. A string just 1 kilometer long might contain as much mass as Earth. Moving such objects would require energy resources approaching the output of entire galaxies. Furthermore, the specific configuration of cosmic strings required for time travel, typically 2 strings moving past each other at high velocities, presents additional challenges. Calculations by Hawking and others suggest that creating a usable time machine this way would require either infinite strings or energy equivalent to the mass of the observable universe, clearly beyond what any civilization could achieve, no matter how advanced. Tipler cylinders and other rotating mass approaches face similar obstacles. Creating a cylinder massive enough and rotating fast enough to generate closed time-like curves would require either an infinitely long cylinder physically impossible, or a finite cylinder with density and rotational speeds that may violate other physical principles. The gravitational forces near such objects would likely tear apart any spacecraft or biological entity unless protected by technologies equally beyond our current understanding. Rotating black holes might seem more promising since they occur naturally, eliminating the need to create extreme spacetime conditions artificially. However, approaching a black hole closely enough to utilize its temporal properties would expose travelers to lethal radiation, tidal forces that would stretch any object into atomic strands, and navigation challenges of extraordinary difficulty. Even if these obstacles could somehow be overcome, recent theoretical work in quantum gravity suggests that the interior structure of black holes may be more complex than indicated by classical general relativity alone. The smooth path through a rotating black hole's ring singularity that appears in mathematical solutions might be disrupted by quantum effects, closing this potential avenue for time travel. Beyond these specific challenges for each approach, all potential time machine designs share certain fundamental limitations. One of the most significant is that none of these theoretical time machines would allow travel to a time before the machine itself was created. You couldn't use them to visit ancient Egypt or witness the dinosaurs. At best, you could return to the moment when the time machine first became operational. This limitation arises because these devices work by creating closed time-like curves in a specific region of spacetime. They don't provide access to arbitrary points in the past. This is quite different from fictional time machines that can target any historical period with precision. Given these formidable challenges, it's reasonable to ask whether time travel to the past will ever be practically achievable, even for civilizations far more advanced than our own. The combination of enormous energy requirements, the need for materials or conditions that may be physically impossible, and potential quantum limitations suggested by the chronology protection conjecture makes it unlikely that human beings, or any other intelligent species, will ever construct a working time machine capable of sending matter or information into the past. However, this assessment applies specifically to travel to the past. Travel to the future, through the time dilation effects we explored earlier, faces no such fundamental obstacles. It emerges naturally from well-verified aspects of special and general relativity and requires only sufficiently advanced propulsion technology to achieve velocities where these effects become significant. To experience substantial time dilation, a spacecraft would need to reach speeds approaching that of light, 299,792,458 meters per second. At 90% of light speed, each year on the spacecraft would correspond to about 2.3 years on Earth. At 99% of light speed, the ratio increases to about 7 years on Earth for each year on the spacecraft. And at 99.9% of light speed, each year aboard the spacecraft would see about 22 years pass on Earth. The challenges of achieving such velocities are enormous, but not insurmountable in principle. Conventional chemical rockets are wholly inadequate for the task, with maximum velocities less than 0.01% of light speed. More advanced propulsion concepts, nuclear pulse propulsion, fusion rockets, antimatter engines, or massive external accelerators, might potentially achieve a few percent of light speed. But even these would require engineering capabilities significantly beyond current technology, reaching truly relativistic speeds above 90% of light speed would require even more exotic approaches. Theoretical concepts like the Bussard ramjet, which would collect interstellar hydrogen as fuel using enormous electromagnetic fields, or beam-powered propulsion, where external laser arrays accelerate a spacecraft with light pressure, have been proposed, but they remain speculative and would require engineering at scales far beyond current capabilities. Beyond the propulsion challenges, relativistic spacecraft would face serious hazards from interstellar gas and dust. At 99% of light speed, each hydrogen atom in the interstellar medium would impact the spacecraft with energy equivalent to high-energy cosmic rays. Shielding against this radiation would add significant mass to the vehicle, further complicating the propulsion requirements. Despite these challenges, future directed time travel through relativistic flight doesn't violate any known physical laws. It's an engineering problem of extraordinary difficulty, not a fundamental impossibility. Given centuries or millennia of technological development, a sufficiently advanced civilization might develop the capabilities required for substantial time dilation journeys. Another approach to practical time manipulation involves what we might call time simulation rather than true time travel. Advanced virtual reality or direct neural interfaces might someday allow people to experience simulated versions of the past or potential futures with such fidelity that they would be experientially indistinguishable from actual time travel. While such simulations wouldn't constitute genuine temporal displacement, they might satisfy many of the motivations behind the desire for time travel: historical research, exploration of alternative histories, reunion with lost loved ones in simulated form, or anticipation of future developments. For many purposes, a perfect simulation might be functionally equivalent to actual time travel from the participant's perspective. Similarly, sufficiently advanced biological technologies might someday allow for negligible senescence or biological immortality, enabling individuals to naturally experience the distant future without requiring relativistic journeys or other temporal manipulation. Combined with suspended animation or cryopreservation technologies, such capabilities might allow people to time travel to the future simply by temporarily suspending their biological processes and reawakening decades or centuries later. These approaches, time dilation through relativistic travel, high-fidelity simulation, and biological suspension, represent potentially achievable forms of future-directed time travel that don't require the extreme space-time manipulations of wormholes or cosmic strings. They work within established physical laws rather than exploiting speculative loopholes in general relativity. But what about travel to the past? Is it fundamentally impossible or merely extraordinarily difficult? This question touches on deep issues in the foundations of physics, particularly the tension between general relativity, which seems to permit closed time-like curves under certain conditions, and quantum mechanics, which might enforce causality through mechanisms like Hawking's chronology protection conjecture. Some physicists have proposed experimental tests of causality and chronology protection using quantum systems. While these experiments wouldn't involve macroscopic time travel, they might reveal whether nature fundamentally forbids closed causal loops at the quantum level, providing indirect evidence about the possibility of larger-scale time machines. For example, theoretical physicist Seth Lloyd has proposed what he calls a quantum time machine, an experiment using quantum teleportation to create a situation where information effectively travels along a closed-to-light curve. The results of such experiments could potentially reveal whether nature imposes a universal chronology protection mechanism or allows limited forms of causality violation. Another approach involves searching for evidence of time travelers through historical or astronomical observations. Various researchers have proposed looking for anachronistic technologies, foreknowledge of future events, or time traveler interventions in historical records. More scientifically, some have suggested searching for evidence of advanced civilizations manipulating cosmic strings, creating wormholes, or generating other signatures of time machine technology that might be detectable across cosmic distances. To date, no convincing evidence of time travelers has been found, which might indicate either that time travel to the past is impossible, that temporal journeys are carefully regulated to prevent detection, or simply that no civilization in our light cone has yet developed the necessary technology. The absence of evidence isn't conclusive, but it aligns with the theoretical arguments suggesting the extreme difficulty of past-directed time travel. So where does this leave the practical prospects for time machine construction? Based on current scientific understanding, we can draw several conclusions. First, time travel to the future through relativistic time dilation is physically possible and requires no exotic physics, just sufficiently advanced propulsion technology. While the engineering challenges are formidable, they don't appear to be fundamentally insurmountable given sufficient technological development. Second, time travel to the past appears to face both theoretical and practical obstacles of extraordinary magnitude. While general relativity doesn't explicitly forbid closed time-like curves, creating the conditions necessary for such curves would require energy resources, materials, and engineering capabilities that may be forever beyond reach, even for far future civilizations. Third, the tension between general relativity, which seems to permit past-directed time travel, and quantum mechanics, which may forbid it through chronology protection, remains unresolved. A full theory of quantum gravity might eventually determine whether closed time-like curves are physically possible or merely mathematical artifacts of an incomplete theory. Fourth, alternative approaches like virtual reality, simulation, suspended animation, or biological life extension might eventually provide experiences functionally similar to time travel for many purposes, without requiring the extreme physics of actual temporal displacement. For those who dream of someday traveling through time, these conclusions might seem disappointing. The time machines of science fiction, devices that allow convenient travel to arbitrary points in the past or future, appear to be physically impossible based on our current understanding. Even the more limited time machines permitted by general relativity would require resources and capabilities so vast that they may remain forever beyond practical realization. Yet the scientific exploration of time travel possibilities has value beyond determining whether such journeys might someday be possible. It functions as a theoretical laboratory for testing the boundaries of our physical theories, revealing potential inconsistencies or unexplored regimes where new physics might emerge. Questions about time travel have driven important developments in our understanding of causality, quantum information, and the relationship between general relativity and quantum mechanics. Moreover, the pursuit of time travel technology, even if ultimately unsuccessful in its primary goal, might yield valuable technological spin-offs. Research into advanced propulsion for relativistic spacecraft could revolutionize space travel within our solar system. Investigations of exotic quantum states relevant to chronology protection might lead to breakthroughs in quantum computing or communication. The history of science is filled with instances where the pursuit of seemingly impossible goals led to unexpected and valuable discoveries along the way. In the absence of functioning time machines, we rely on other methods to explore the past and anticipate the future. Historical research, archaeology, and geology allow us to reconstruct what happened before our time. Predictive modeling, trend analysis, and scenario planning help us prepare for what might lie ahead. While these approaches lack the immediacy and certainty of actual time travel, they represent our best available tools for temporal exploration. Perhaps someday, a breakthrough in theoretical physics will reveal a simpler approach to time travel than the extreme methods we've discussed. An unexpected loophole in space-time that can be exploited with relatively modest technology. History is filled with instances where the seemingly impossible became routine through unexpected insights or approaches. Until such a breakthrough occurs, however, time travel remains primarily in the realm of fascinating theoretical speculation rather than practical technology. We can currently manipulate time only in the limited sense of time dilation effects, creating small differences in aging between differently moving observers. More dramatic temporal journeys, particularly to the past, appear to face obstacles so formidable that they may forever remain beyond our reach. Yet the questions raised by time travel research continue to drive exploration at the frontiers of fundamental physics. By contemplating what would happen if we could move freely through time, we gain insights into what time actually is. And these insights sometimes challenge our most basic intuitions about how the universe works. As we transition to our next topic, the more achievable prospect of traveling to the future through relativistic effects, we should appreciate the intellectual journey that time travel speculation has taken us on. From Einstein's revolutionary insights about the relativity of simultaneity to cutting-edge research on quantum gravity and causality, the question of whether time travel is possible has repeatedly pushed us to deeper understanding of nature's fundamental principles. And in this ongoing quest for understanding, perhaps we find a form of time travel after all. Not physical displacement through time, but the mind's remarkable ability to reconstruct the past and anticipate the future, to learn from history and prepare for what lies ahead. While we may never physically visit the bygone days of ancient civilizations or witness the distant future of our species, the human capacity for temporal imagination allows us to explore the fourth dimension in ways that transcend the physical limitations of our three-dimensional existence. For now, at least, this mental time travel, enhanced by science, history, and informed speculation, remains our primary means of exploring temporal realms beyond our immediate present. And while it lacks the drama of stepping into a time machine, it nonetheless offers a form of temporal transcendence that has enriched human culture and understanding throughout our history as a species. While journeys to the past remain mired in theoretical paradoxes and seemingly insurmountable engineering challenges, traveling to the future represents a more promising avenue for potential time travelers. Unlike past-directed time travel, which requires exotic physics and may be fundamentally impossible, future-directed travel emerges naturally from well-established principles of relativity. In this section, we'll explore how humanity might someday develop the capability to leap forward through time, witnessing eras far beyond our own lifespans. The key to understanding future time travel lies in Einstein's theories of relativity and the resulting phenomenon of time dilation. As we've discussed in earlier sections, time passes at different rates depending on the relative motion and gravitational potential. These differences can be exploited to experience what amounts to time travel into the future, arriving at a future date, having aged far less than those who remained in a reference frame at rest. Let's examine the practical possibilities for such journeys, beginning with the most well-established approach, relativistic time dilation through high-velocity travel. The mathematics of special relativity shows that as an object approaches the speed of light, time for that object passes more slowly relative to stationary observers. This effect is governed by what physicists call the Lorentz factor, represented by the Greek letter gamma, gao, which quantifies exactly how much time slows down at a given velocity. At 50% of light speed, the time dilation factor is about 1.1, meaning that for every 1.15 years passing on Earth, only 1 year would pass for travelers at this velocity. While noticeable, this level of time dilation wouldn't create dramatic temporal jumps. However, as velocity increases, the effect becomes increasingly pronounced. At 90% of light speed, each year aboard the spacecraft would correspond to about 2.3 years on Earth. At 99% of light speed, the ratio increases to about 7 years on Earth for each year on the spacecraft. And at 99.9% of light speed, each year aboard the spacecraft would see about 22 years pass on Earth. Push the velocity even closer to the speed of light, and the time dilation becomes truly dramatic. At 99% of light speed, the spacecraft experiences only 1 year, while 70 years pass on Earth, effectively allowing the crew to travel 7 decades into the future during what subjectively feels like a single year. At 99% of light speed, The factor increases to about 224 years on Earth for each year on the spacecraft. These aren't mere theoretical calculations, but direct consequences of relativistic physics that have been confirmed experimentally, albeit on smaller scales. Subatomic particles accelerated to near light speed in particle accelerators regularly demonstrate precisely these time dilation effects, living far longer than their stationary counterparts due to their relativistic velocities. The engineering challenges of achieving such speeds for macroscopic objects like spacecraft are formidable, but not theoretically impossible. Conventional chemical rockets are wholly inadequate for relativistic travel, with maximum velocities less than 0.01% of light speed. Even our fastest current spacecraft, like NASA's Parker Solar Probe, which will eventually reach speeds of about 690,000 kilometers per hour, or 0.064% of light speed, fall far short of velocities that would create significant time dilation. More advanced propulsion concepts would be required to achieve relativistic speeds. Nuclear pulse propulsion, essentially detonating a series of nuclear explosives behind a spacecraft equipped with a massive shield, could theoretically achieve speeds of 3 to 5% of light speed. While this would create measurable time dilation, with each year aboard the spacecraft corresponding to about 1.001 years on Earth, it's not enough for dramatic temporal jumps. Fusion rockets, antimatter engines, or beam-powered propulsion might potentially achieve 10 to 20% of light speed with sufficiently advanced technology, but even these would create relatively modest time dilation effects. Reaching truly relativistic speeds, above 90% of light speed, where time dilation becomes dramatic, would require even more exotic approaches. Theoretical concepts like the Bussard ramjet, which would collect interstellar hydrogen as fuel using enormous electromagnetic fields, or extreme forms of beam-powered propulsion, where massive laser or maser arrays accelerate a spacecraft with light pressure, have been proposed. However, they remain highly speculative and would require engineering at scales far beyond current capabilities. The energy requirements for relativistic travel are particularly daunting. Accelerating a 1,000-ton spacecraft to 99% of light speed would require energy equivalent to the entire world's electricity production for hundreds of years at current levels. Even with far more efficient propulsion systems than anything we currently possess, the energy demands would be enormous. Beyond propulsion challenges, relativistic spacecraft would face serious hazards from interstellar gas and dust. At 99% of light speed, each hydrogen atom in the interstellar medium would impact the spacecraft with energy equivalent to high-energy cosmic rays. Even the sparse material between stars would become a serious radiation threat at such velocities, requiring substantial shielding that would add mass to the vehicle and further complicate the propulsion requirements. Despite these challenges, relativistic time travel doesn't violate any known physical laws. It's an engineering problem of extraordinary difficulty, not a fundamental impossibility. Given centuries or millennia of technological development, a sufficiently advanced civilization might develop the capabilities required for substantial time dilation journeys. Interestingly, there's a cosmic speed limit that prevents us from achieving infinite time dilation. Nothing with mass can reach the speed of light itself. As an object with mass accelerates toward light speed, it requires increasingly more energy for smaller and smaller increases in velocity, approaching infinite energy requirement at light speed itself. This limitation, fundamental to relativity, means that while we can achieve very large time dilation factors by approaching light speed extremely closely, we can never achieve infinite time dilation or instantaneous travel to the distant future. An alternative approach to relativistic travel for future-directed time travel involves exploiting gravitational time dilation rather than velocity-based effects. As Einstein's general relativity demonstrates, time passes more slowly in stronger gravitational fields. This effect has been precisely measured using atomic clocks at different altitudes on Earth and is a crucial consideration for systems like GPS satellites. Near extremely massive objects like black holes, this gravitational time dilation becomes dramatic. A spacecraft orbiting just outside the event horizon of a supermassive black hole could experience time at a rate hundreds or thousands of times slower than distant observers. 1 year for the crew might correspond to centuries or millennia for civilization on Earth. The film Interstellar depicted this phenomenon when astronauts visited a planet orbiting near a black hole named Gargantua. Due to the intense gravitational field, each hour spent on the planet corresponded to 7 years passing on their orbiting spacecraft, and even longer on Earth. While the film took some creative liberties, its portrayal of gravitational time dilation was based on solid physics, with noted theoretical physicist Kip Thorne serving as a scientific consultant. Using black holes for time travel would present enormous challenges, however. Approaching a black hole closely enough for significant time dilation would expose travelers to intense gravitational gradients, tidal forces, that could tear apart a spacecraft or human body unless protected by technologies far beyond our current capabilities. The intense radiation near black holes, from infalling matter heated to millions of degrees, would present additional hazards requiring extraordinary shielding. Moreover, black holes present a one-way journey in more ways than one. The gravitational well of a black hole is so deep that escaping it after approaching closely enough for significant time dilation would require energy resources far beyond what we can currently contemplate. And of course, crossing the event horizon would make escape impossible by definition, the ultimate one-way trip. Despite these challenges, black hole time dilation represents another physically valid mechanism for future directed time travel based on established physics, rather than speculative exotic phenomena. Like relativistic travel, it's an engineering problem of extraordinary difficulty rather than a fundamental impossibility. Beyond these physics-based approaches, biological methods might someday provide alternative pathways to experiencing the future. Suspended animation, the temporary and reversible slowing or stopping of biological processes, would allow individuals to skip over intervening years while aging minimally. While not true time travel in a physical sense, the subjective experience would be similar, entering a suspended state and awakening in the future. Current cryopreservation technologies can preserve biological tissues by replacing water with cryoprotectant solutions and cooling to extremely low temperatures, typically around -196 degrees Celsius, the temperature of liquid nitrogen. However, existing methods cannot yet reversibly preserve whole human bodies without causing fatal damage during the freezing and thawing processes. The damage to cell membranes, tissues, and organs from ice crystal formation remains a significant obstacle. More sophisticated approaches to suspended animation are being researched, including metabolic depression through hydrogen sulfide exposure, which works in mice but has shown limited success in larger mammals. Synthetic hibernation using targeted temperature management, and various cryoprotectant combinations that minimize ice crystal formation. While current technology falls far short of the suspended animation depicted in science fiction, ongoing research suggests that more advanced capabilities might eventually be developed. If perfected, such technologies could allow individuals to effectively travel hundreds or thousands of years into the future while experiencing only a brief subjective interval, a form of biological time dilation without the need for relativistic velocities or extreme gravitational fields. Taking this concept further, advances in longevity research might someday enable biological immortality or negligible senescence, essentially eliminating aging as a cause of death. Combined with sufficient medical technology to repair injuries and combat disease, such capabilities would allow individuals to naturally live long enough to witness future eras that would otherwise lie beyond their lifespans. While this isn't time travel in the physics sense, it would achieve the same fundamental goal, experiencing a future far beyond one's natural lifetime. Current longevity research focuses on understanding and potentially modifying the fundamental biological mechanisms of aging, including telomere shortening, mitochondrial dysfunction, cellular senescence, and epigenetic alterations. while significant life extension for humans remains beyond current capabilities. Rapid advances in genetic engineering, regenerative medicine, and biotechnology suggest that substantial progress might be possible within coming decades or centuries. Whether through physics-based approaches like relativistic travel and gravitational time dilation, or biological methods like suspended animation and life extension, the prospect of experiencing the future beyond our natural lifespans appears scientifically plausible, if technically challenging. Unlike travel to the past, future-directed travel doesn't create logical paradoxes or require exotic physics beyond established scientific principles. This fundamental asymmetry between past and future travel reflects the arrow of time itself, the universe's apparent preference for one temporal direction over the other. While the fundamental laws of physics work equally well running forward or backward in time, the second law of thermodynamics introduces an asymmetry through entropy's relentless increase. This may be why future travel seems physically permissible, while past travel faces both practical and theoretical obstacles that may be insurmountable. But what would it mean to travel to the future? What might time travelers discover in eras far beyond our own? While we can't know with certainty what awaits in distant times, we can make educated extrapolations based on scientific understanding of cosmic evolution and human development. In the relatively near future, centuries or a few millennia hence, time travelers would likely find a human civilization transformed by technologies we can barely imagine. If humanity survives its current challenges and continues technological development, future centuries could witness post-scarcity economies, artificial general intelligence far surpassing human capabilities, merging of biological and technological systems, expansion throughout our solar system, and perhaps beyond to neighboring stars. Travelers jumping tens of thousands of years ahead might find humanity unrecognizably transformed, perhaps having engineered its own biological nature, merged consciousness with artificial systems, or diverged into multiple species, adapted to different environments throughout space. Whether such transformations would represent advancement or decline from our perspective would depend on the choices our descendants make and the values they embrace. Leaping millions of years into the future would reveal more dramatic changes. Earth itself would look different due to continental drift, climate shifts, and evolutionary changes in flora and fauna. The sun would be slightly hotter and brighter as part of its natural stellar evolution. Humanity, if it still exists in any recognizable form, would likely have spread far beyond Earth, perhaps engineering entire solar systems to meet its needs. Truly extreme temporal jumps, billions of years forward, would reveal cosmic changes beyond human influence. 5 billion years hence, our sun will have exhausted its core hydrogen, expanded into a red giant, and potentially engulfed Earth's orbit. After another several hundred million years, it will shed its outer layers and collapse into a white dwarf, a dense ember that will slowly cool over trillions of years. The ultimate future of the universe itself depends on its overall structure and the nature of dark energy. Under current models, cosmic expansion will continue accelerating, eventually pulling galaxies beyond each other's visible horizons. After approximately 100 trillion years, star formation will cease as the available gas becomes too diffuse for gravitational collapse. Existing stars will gradually die out, leaving a universe increasingly dominated by black holes, which themselves will eventually evaporate through Hawking radiation over incomprehensibly long timescales, approximately 10 to the power of 100 years for the largest supermassive black holes. Time travelers journeying to such remote futures would find a cold, dark cosmos approaching what physicists call the heat death, a state of maximum entropy where no further work or organized activity is possible. Whether conscious beings of any kind could survive in such an environment, perhaps using the remaining energy gradients from black hole evaporation or quantum fluctuations, remains speculative. This cosmic perspective highlights an important aspect of future-directed time travel. It's a one-way journey. While relativistic or gravitational time dilation can propel travelers forward in time, No known physical mechanism allows return to the original time period. Once you've witnessed Earth 1,000 years hence, you can't go back to report what you've seen. You're stranded in that future era. This limitation has profound implications for potential time travelers and the societies that might develop such technologies. Would people volunteer for missions knowing they could never return to the world they knew? How would future societies react to visitors from the distant past? Would time-dilated travel become a form of extreme tourism for the adventurous, a scientific endeavor, or perhaps even a desperate escape from civilizational catastrophe? The one-way nature of future travel also creates an information asymmetry. Knowledge can flow from past to future, but not in reverse. Time travelers could bring historical knowledge forward, but couldn't return with information about future developments. This asymmetry aligns with our everyday experience of time. We remember the past, but can only speculate about the future, and may represent a fundamental limitation that even advanced technology cannot overcome. Despite this limitation, the prospect of future-directed time travel holds tremendous scientific and philosophical significance. It would allow observers to witness evolutionary changes, geological processes, and cosmic developments that normally unfold too slowly for human perception. It would provide direct observational data about humanity's long-term development and ultimate fate, and it would offer perspective on our current moment in cosmic history, our brief window in the universe's vastly longer timeline. For individual travelers, such journeys would offer experiences beyond ordinary human comprehension. Imagine witnessing Earth 1,000,000 years hence, seeing evolved species and landscapes transformed by geological processes. Imagine observing the fate of human civilization, whether triumphant expansion throughout the cosmos or eventual extinction. Imagine watching the death of our sun billions of years in the future, as it expands into a red giant before collapsing to a white dwarf. These vistas across deep time would transform our understanding of ourselves and our place in the universe. Of course, such experiences would come at enormous personal cost. Time travelers would leave behind everything familiar: friends, family, culture, society. They would become living anachronisms, their knowledge increasingly irrelevant as they moved further forward through time. The psychological impact of such temporal dislocation would likely be profound, perhaps comparable to the culture shock experienced by individuals suddenly transported between radically different societies. These considerations raise ethical questions about future-directed time travel that go beyond the technical challenges. Is it responsible to send people on one-way journeys to unknown futures? What obligations would we have to time travelers stranded in our era? Could the knowledge they bring forward, even accidentally, disrupt technological or social development in unforeseen ways? Despite these complexities, future-directed time travel remains one of the most tantalizing possibilities suggested by modern physics. Unlike travel to the past, it doesn't obviously violate causality or create logical paradoxes. It emerges naturally from well-verified aspects of relativity rather than requiring exotic physics or speculative loopholes in space-time. And while the engineering challenges are formidable, they appear to be matters of technical capability rather than fundamental physical impossibility. Perhaps someday, humans or their descendants will develop the technologies required for significant time dilation journeys, whether through relativistic spacecraft approaching light speed, habitats orbiting near black holes, advanced suspended animation, radical life extension, or approaches we haven't yet conceived. These temporal pioneers would experience what generations before them could only imagine: direct observation of futures far beyond their natural lifespans. For now, we remain anchored in our present moment, able to move into the future only at the standard rate of 1 second per second. Yet through scientific understanding, we can at least envision what might someday be possible, and appreciate the remarkable fact that future-directed time travel, while enormously challenging, doesn't appear to be fundamentally forbidden by the laws of physics as we currently understand them. As we prepare to explore the deeper philosophical questions about time's fundamental nature in our next section, we carry forward this crucial insight. The future, at least, appears to be accessible through sufficiently advanced technology. While we may never be able to revisit the past, the mysterious realm of future time may someday open to human exploration, offering vistas across cosmic timescales that now we can only imagine. In closing this section, it's worth reflecting on an intriguing possibility. Perhaps future-directed time travelers already exist. If civilization survives long enough to develop the necessary technologies, individuals might someday be routinely dispatched to witness important historical eras, including our own. Unable to return to their point of origin, these temporal emigrants would likely attempt to integrate into the societies they visit, becoming indistinguishable from ordinary humans of the era. While this speculation veers towards science fiction, it highlights an asymmetry between past and future travel. If only future-directed travel is possible, we would never be visited by people from our future, but our distant descendants might someday observe us through temporal displacement. Whether such observation is already occurring remains, of course, entirely speculative, but the possibility emerges naturally from the physics we've explored throughout this section. Throughout our exploration of time travel possibilities, we've approached time as a fundamental dimension of reality, something that flows steadily forward, carrying the universe from past to future, even if that flow can be dilated or potentially manipulated under extreme conditions. But what if our intuitive understanding of time is fundamentally mistaken? What if time as we experience it, the clear distinction between past, present and future, the sense of moments passing in sequence, is not a basic feature of reality, but rather an illusion created by our minds? This provocative question lies at the intersection of physics, philosophy, neuroscience, and human experience. It challenges our most basic assumptions about reality and our place within it. And it may hold profound implications for the possibility of time travel and our understanding of the cosmos. Let's begin by examining what modern physics tells us about time's fundamental nature. When Einstein unified space and time into a four-dimensional space-time continuum through his theories of relativity, he introduced a perspective that differs radically from our everyday experience. In relativistic physics, time is not an independent dimension flowing uniformly throughout the universe, but rather an integral part of a four-dimensional structure whose properties vary depending on motion and gravity. This relativistic view led Einstein to a profound insight about time's nature, expressed in a letter to the family of his deceased friend, Michel Besso. Now he has departed from this strange world a little ahead of me. That means nothing. People like us, who believe in physics, know that the distinction between past, present, and future is only a stubbornly persistent illusion. This statement reflects what physicists call the block universe, or eternalist view, the conception that past, present, and future all exist simultaneously in a four-dimensional spacetime block. From this perspective, the universe is not evolving from moment to moment. Rather, it's a complete four-dimensional structure where all events, past, present, and future, exist permanently. Our experience of time flowing is merely a perspective effect arising from our limited three-dimensional perception as we move along our world lines through this four-dimensional reality. The mathematician Hermann Minkowski, who formalized the mathematics of spacetime, expressed this view when he declared, "Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." In the block universe model, time doesn't flow any more than space does. Just as all points in space exist simultaneously, all moments in time exist permanently. The apparent passage of time is analogous to the illusion of movement created when we travel along a road. The landscape doesn't actually change or flow. We simply encounter different parts of it sequentially. This view receives support from the mathematical structure of our most successful physical theories. The equations of both relativity and quantum mechanics are time-symmetric. They work equally well whether time runs forward or backward. Nothing in these fundamental equations suggests a privileged now, or indicates that time flows in one direction rather than another. The clear arrow of time we experience, with entropy increasing and causes preceding effects, doesn't appear to be built into the basic laws of physics. If this block universe view is correct, time travel takes on a different conceptual meaning. Rather than changing something that's dynamic and flowing, time travelers would simply be taking non-standard paths through an already existing four-dimensional structure. They wouldn't be changing the past or future, which exist permanently in this model, but merely accessing different regions of space-time via routes other than the typical 1 second per second journey that most objects follow. This perspective might resolve some of the paradoxes we explored earlier. In a block universe, you can't change the past because the past isn't something malleable. It's a fixed region of space-time. Any journey to the past would simply be fulfilling events that are already part of the four-dimensional whole. The grandfather paradox dissolves because any action a time traveler takes in the past must be consistent with the fact that they exist to make the journey in the first place, creating a self-consistent causal loop rather than a genuine paradox. However, the block universe view faces significant challenges. If all of time exists at once, why do we experience it flowing in one direction? Why do we remember the past but not the future? Why does entropy increase in one temporal direction but not the other? These questions point to an apparent asymmetry in time that isn't easily explained if past, present, and future are all ontologically equivalent. Moreover, the block universe seems to leave little room for free will or genuine becoming. If the future already exists in the same sense that the past does, our actions aren't truly creating that future, but merely playing out a script that's already written in the four-dimensional structure of space-time. This deterministic implication troubles many philosophers and has led some physicists to seek alternative frameworks. One such alternative is presentism, the view that only the present moment truly exists, with the past gone and the future not yet formed. In this view, reality consists solely of what exists now, and time's passage represents the continuous creation of new presents as old ones cease to exist. While this aligns better with our subjective experience, it struggles to reconcile with relativistic physics, particularly the relativity of simultaneity, the fact that observers in different reference frames disagree about which events are simultaneous, and thus about what constitutes now. Between these extremes lie various intermediate positions. Growing block theory suggests that the past and present exist, but the future does not. Reality continuously grows as present moments become past. Branching space-time theories allow for multiple possible futures stemming from each present moment, creating a tree-like structure rather than a single determined timeline. These philosophical perspectives on time have been complemented in recent years by insights from neuroscience and cognitive psychology about how our brains process temporal information. These studies suggest that our perception of time's flow may indeed be a construction of the mind, rather than a direct apprehension of an external reality. Our brains don't actually perceive time directly as they do light or sound. Instead, they construct a sense of temporal sequence by integrating various sensory inputs, comparing them with memories, and creating a coherent narrative of change and continuity. This constructed nature of temporal perception is revealed by numerous temporal illusions, instances where our perception of time's duration or sequence diverges from objective measurement. For example, experiments show that our brains often register the consequences of our actions before we become consciously aware of deciding to act, suggesting that our sense of initiating actions in real time may be a retrospective construction rather than an accurate perception of causal sequence. Other studies demonstrate that attention, emotion, and expectation can dramatically alter our perception of time's passage, with moments of danger seeming to unfold in slow motion or periods of enjoyment seeming to fly by. These findings have led some neuroscientists to propose that our experience of time flowing from past to future, with a special now moving along this stream, is fundamentally a useful fiction created by our brains, an evolutionary adaptation that helps us navigate the world rather than a direct perception of time's true nature. The philosopher Immanuel Kant anticipated this view centuries ago arguing that time is not a feature of things in themselves, but rather a form of intuition that our minds impose on our experience of the world. In this Kantian perspective, we cannot perceive reality without the framework of time, but time itself is not an objective feature of reality independent of our perception. More recently, the neuroscientist David Eagleman has suggested that our sense of now actually spans about 100 milliseconds of physical time, within which our brains integrate information received at different speeds from different senses to create the illusion of a unified present moment. Events occurring within this window of simultaneity are experienced as happening at the same time, even if they're physically separated by tens of milliseconds. These neuroscientific perspectives don't prove that time is an illusion in the metaphysical sense, but they suggest that our subjective experience of time, the feeling of being located at a moving now, with the past behind and the future ahead, may not accurately reflect the fundamental nature of temporal reality. Moving from human perception to more fundamental levels, quantum mechanics introduces additional complexities to our understanding of time. In the famous delayed choice quantum eraser experiments, the decision to measure certain properties of a particle appears to retroactively determine the behavior of related particles in the past. While these experiments don't allow for the transmission of information backward in time, thus preserving causality in a practical sense, they suggest a reality where temporal ordering may be more flexible than our classical intuitions allow. Some interpretations of quantum mechanics, like John Wheeler's participatory universe, suggest that observation in the present can in some sense create the past, rather than merely revealing what already happened. In Wheeler's words, the past has no existence, except as it is recorded in the present. This view challenges the notion that the past exists in a fixed, determined form, independent of current observations. Taking quantum considerations to their logical conclusion, theoretical physicist Carlo Rovelli has developed what he calls relational quantum mechanics, in which time, like other physical properties, has no absolute existence, but only manifests in the interactions between systems. In this view, there is no universal now or global time parameter. Time emerges from relationships between physical systems rather than existing as an independent dimension. Rovelli's related thermal time hypothesis suggests that the apparent flow of time emerges from quantum entanglement between systems with many degrees of freedom. Rather than being fundamental, time's arrow would be a statistical effect arising from the way information flows between entangled systems. This perspective aligns with approaches to quantum gravity that suggest space-time itself may emerge from more fundamental quantum processes rather than being a basic framework within which those processes occur. Another provocative view comes from theoretical physicist Julian Barber, who argues in his book The End of Time that time doesn't exist as a dimension or flow at all. Instead, what we perceive as temporal sequence is actually relationships between different complete configurations of the universe, what Barber calls time capsules. Each possible configuration of the universe exists as a distinct now that contains within it records of other configurations that we interpret as past events. The apparent flow from one moment to another is an illusion arising from the way our consciousness connects these static configurations. In Barber's view, the universe is not a four-dimensional block with time as the fourth dimension, but rather a vast collection of three-dimensional nows with no temporal dimension connecting them. Time travel would be conceptually impossible in such a framework since time itself doesn't exist as a dimension through which one could move. A related perspective comes from the holographic principle in theoretical physics, which suggests that our apparently three-dimensional spatial reality may be encoded on a two-dimensional boundary, similar to how a hologram encodes three-dimensional information on a two-dimensional surface. Extended to include time, this raises the possibility that our four-dimensional space-time might be a projection from a more fundamental reality with different dimensional properties. These speculative frameworks from the frontiers of theoretical physics suggest that time as we understand it may not be a basic feature of reality at the deepest level. Instead, what we experience as temporal flow might emerge from more fundamental quantum processes, information relationships, or dimensional projections that don't themselves involve time in the familiar sense. If time is indeed emergent rather than fundamental, a useful approximation that works at the macroscopic level but breaks down under extreme conditions or at the most basic scales. This would have profound implications for time travel. You can't travel through a dimension that doesn't fundamentally exist. Time machines might be impossible, not because of engineering limitations or paradoxes, but because they're premised on a misconception about reality's basic structure. On the other hand, if time emerges from more fundamental processes, understanding those processes might eventually allow manipulation of temporal effects in ways we currently can't imagine, not through brute force engineering of space-time, but through subtle interventions in the underlying mechanisms from which time emerges. Theoretical physicist Lee Smolin offers a contrasting perspective in his temporal naturalism, arguing that time is not only real but fundamental, the primary reality from which space and matter emerge, rather than a secondary feature of a more basic spatial reality. In Smolin's view, the passage of time and the emergence of genuine novelty are essential features of our universe, not illusions to be explained away. While this approach faces its own challenges in reconciling with established physics, it provides a philosophical alternative to the block universe that aligns more closely with our intuitive experience of time. These diverse perspectives, from the block universe of relativity to the emergent time of quantum gravity, from the neurological construction of temporal experience to the philosophical debates about time's fundamental nature, remind us how little we truly understand about this most familiar yet mysterious dimension of our existence. Time may be fundamental or emergent, real or illusory, flowing or static, and our current scientific understanding, advanced as it is, doesn't definitively resolve these possibilities. What are the implications of these considerations for the prospect of time travel? If time is indeed an illusion in some deep sense, not a dimension through which we could move, but an emergent property, a mental construction or a statistical effect, then physical time travel, as typically conceived, might be fundamentally impossible. You can't travel through something that doesn't exist as a navigable dimension. However, this wouldn't necessarily rule out experiences that functionally resemble time travel. If our perception of temporal sequence is constructed by our brains, future technologies might potentially alter this construction, creating subjective experiences of visiting the past or future, even without physical displacement through time. Advanced virtual reality, direct neural interfaces, or technologies we cannot yet imagine might someday create experiences indistinguishable from actual time travel from the participant's perspective. Similarly, if time emerges from more fundamental quantum processes or information relationships, understanding and manipulating those underlying mechanisms might eventually allow for effects that appear temporal in nature, potentially including limited forms of information transfer or causal influence across what we perceive as temporal boundaries. The uncertainty about time's fundamental nature also suggests a certain epistemic humility regarding the possibility of time travel. Throughout history, capabilities once thought physically impossible have sometimes become reality through deeper understanding of nature's principles, often working with nature's laws rather than against them. If our current conception of time is incomplete or fundamentally mistaken, future developments might reveal possibilities we currently cannot imagine. For now, this exploration of time's nature brings us full circle in our journey through the physics of time travel. We began by considering time as a dimension that might be traversed under the right conditions. We then explored specific mechanisms, from wormholes to relativistic flight, that might potentially allow such traversal. We confronted the paradoxes and practical challenges these approaches would face, and now we've questioned whether time itself might be different from our intuitive understanding, potentially changing the very meaning of time travel. Throughout this journey, we've seen that the simple question, "Is time travel possible?" has no simple answer. travel to the future through time, dilation appears physically possible, though technically challenging. Travel to the past seems fraught with both practical obstacles and logical paradoxes, though some theoretical frameworks might permit it under highly specific conditions. And if time itself is an emergent phenomenon or perceptual construction rather than fundamental dimension, the very concept of time travel might require fundamental reconceptualization. What remains constant across these considerations is the profound mystery of time itself. Despite being our most familiar dimension, the background against which all our experiences unfold, time may be the aspect of reality we least understand. It sits at the intersection of our most successful physical theories, at the boundary between objective reality and subjective experience, at the frontier where physics meets philosophy and neuroscience. The quest to understand time's nature continues at the forefront of modern physics, with approaches ranging from quantum gravity to cosmology to the foundations of quantum mechanics. This ongoing research may eventually resolve whether time is fundamental or emergent, flowing or static, real or illusory. And in doing so, it may finally determine whether journeys through time could ever move beyond the realm of fascinating speculation into physical possibility. As we contemplate these profound questions about time's nature, we might find wisdom in the words of physicist John Archibald Wheeler. Time is what prevents everything from happening at once. This simple observation captures something essential about time's role in our experience. It creates order, sequence, and narrative in what might otherwise be an undifferentiated jumble of existence. Whether this ordering function reflects a fundamental feature of reality or an emergent property, whether time flows objectively or only in our minds, it shapes every aspect of our existence. We live in and through time, marking our lives by its passage, organizing our activities according to its rhythm, creating meaning through the stories it allows us to tell. Perhaps time travel fascinates us not merely for its technological possibilities, but for what it represents. Transcendence of one of the most basic limitations of the human condition. To travel through time would be to break free from our temporal confines, to witness what came before and what will come after, to expand our perspective beyond the narrow window of the present. Even if physical time travel remains forever beyond our reach, the contemplation of its possibilities stretches our minds and expands our understanding. By questioning whether we could journey through time, we deepen our appreciation of what time itself might be, and in doing so, we gain perspective on our place within the vast temporal expanse of cosmic history. The question of whether time is an illusion doesn't diminish its importance in our lives. Even if time proves to be emergent rather than fundamental, a construction of our minds rather than an independent dimension, it remains the medium through which we experience reality. In this sense, time is no more an illusion than the solidity of the chair you're sitting on, which ultimately resolves into mostly empty space at the atomic level, yet remains perfectly real in terms of our everyday experience. As we conclude this exploration of time's nature, we return to Einstein's insight that the distinction between past, present, and future is only a stubbornly persistent illusion. Whether or not we interpret this statement literally, it reminds us that our intuitive understanding of time may not capture its deepest reality. The universe may be stranger, more unified, and more holistic than our time-bound perception suggests. This perspective invites us to consider that we may already be time travelers of a sort, moving through the fourth dimension at the rate of 1 second per second, experiencing the continuous unfolding of reality in the only way our evolved minds can process it. While this ordinary temporal journey lacks the drama of science fiction time machines, it nevertheless represents a remarkable voyage through the mysterious dimension we call time. And perhaps there's wisdom in embracing the journey we're already on, appreciating each moment as it unfolds, recognizing the precious finite nature of our temporal experience, and finding meaning not in escaping time's flow, but in moving with it mindfully and purposefully. For while the physics of time travel offers fascinating possibilities for the distant future, The present moment remains our actual home, the only point from which we can act, create, connect, and find meaning in our brief but wondrous journey through the cosmic timeline. Throughout our journey exploring the physics of time travel, we've traversed terrain ranging from well-established science to speculative frontiers, from practical engineering challenges to profound philosophical questions. We've seen how Einstein's theories revolutionized our understanding of time, examined exotic space-time geometries that might permit temporal journeys, confronted the paradoxes that arise when contemplating travel to the past, and questioned whether time itself might be different from our intuitive understanding. As we conclude this exploration, let's reflect on what current science tells us about the future prospects for time travel and the ongoing quest to understand time's deepest nature. The scientific investigation of time travel has evolved dramatically since H.G. Wells published The Time Machine in 1895. What began as pure science fiction has gradually moved into the realm of serious theoretical physics, with mathematical solutions to Einstein's field equations revealing potential pathways through time. While practical time machines remain beyond our current technological capabilities and may face fundamental obstacles that render them permanently impossible, the theoretical exploration continues to yield insights into the nature of space-time, causality, and reality itself. Based on our current scientific understanding, we can draw several conclusions about the prospects for different forms of time travel. Travel to the future through relativistic time dilation represents the most firmly established possibility. The physics behind this approach, special and general relativistic time dilation, has been experimentally verified countless times, from particle accelerators to atomic clocks at different altitudes. There's no doubt that time passes at different rates depending on relative velocity and gravitational potential. The challenges for this form of time travel lie not in the underlying physics, but in the enormous practical difficulties of achieving velocities or gravitational conditions where the effect becomes significant on human timescales. While current technology falls far short of the capabilities required for dramatic time dilation, these limitations appear to be matters of engineering rather than fundamental physical impossibility. Given sufficient technological advancement, perhaps over centuries or millennia, humanity might eventually develop the capabilities for substantial future-directed temporal jumps. Travel to the past presents more fundamental challenges, while general relativity appears to permit closed time-like curves under certain exotic conditions, potentially allowing journeys to the past. These theoretical possibilities face both practical and conceptual obstacles of extraordinary magnitude. Creating the conditions necessary for closed time-like curves would require energy resources, exotic matter, or space-time configurations that may be physically impossible even in principle, not merely beyond current technology. Moreover, the logical paradoxes associated with past-directed time travel, especially the grandfather paradox, suggest that such journeys might be forbidden by deeper principles not yet fully incorporated into our physical theories. Stephen Hawking's chronology protection conjecture proposes that the laws of physics somehow conspire to prevent closed time-like curves from forming, making travel to the past impossible and preserving causality. While this conjecture remains unproven, the absence of time travelers from the future provides circumstantial support for the idea that past-directed travel may indeed be fundamentally impossible. The tension between general relativity, which seems to permit closed time-like curves under certain conditions, and quantum mechanics, which might forbid them through mechanisms like Hawking's conjecture, highlights a broader issue. Our understanding of time at the deepest level remains incomplete. The reconciliation of quantum mechanics and general relativity into a comprehensive theory of quantum gravity represents one of the great unresolved challenges in theoretical physics, and the nature of time stands at the heart of this challenge. Various approaches to quantum gravity, from string theory to loop quantum gravity to causal set theory, offer different perspectives on time's fundamental nature. Some suggest that space-time itself, including the temporal dimension, emerges from more basic quantum processes rather than serving as a fundamental framework. Others propose that time might be quantized at the Planck scale, approximately 10 to the power of negative 43 seconds, with discrete atoms of time rather than a continuous flow. Still others explore whether time might be a redundant concept at the most fundamental level, with temporal relationships emerging statistically from timeless quantum states. These theoretical explorations at the frontiers of physics suggest that our current understanding of time may be incomplete or fundamentally limited. Time travel might be impossible not because of specific barriers within our current theories, but because time itself works differently than we currently understand. Alternatively, deeper understanding of time's nature might eventually reveal possibilities for temporal manipulation that we cannot currently envision, perhaps not through brute force engineering of space-time, but through subtle interventions in the quantum processes from which time emerges. While definitive resolution of these questions likely lies in the distant future, ongoing research in multiple fields continues to advance our understanding of time and the possibility of temporal journeys. Theoretical physicists develop increasingly sophisticated models of exotic space-time configurations, seeking to determine whether closed time-like curves can exist in physically realistic scenarios, and what constraints quantum effects might impose on such configurations. Experimentalists devise increasingly precise tests of relativistic time dilation and other temporal effects, pushing the boundaries of measurement and potentially revealing unexpected phenomena. The development of optical lattice atomic clocks with precision measuring time differences of 1 in 10 to the power of 18, equivalent to losing less than 1 second over the age of the universe, provides tools for testing relativistic effects with unprecedented accuracy. Astronomers search for natural phenomena that might exhibit extreme temporal properties, from the space-time distortions near black holes to potential signatures of cosmic strings or other exotic structures. The breakthrough detection of gravitational waves in 2015 opened a new window on the dynamic behavior of space-time itself, potentially allowing future observations of phenomena relevant to temporal physics. Quantum information theorists explore the limits of causality in quantum systems, investigating whether quantum effects might allow limited forms of information transfer that appear to violate classical temporal ordering while remaining consistent with relativistic causality. Experiments like the quantum delayed choice and quantum causal order tests probe the boundaries between quantum weirdness and actual temporal manipulation. Computer scientists and artificial intelligence researchers develop increasingly sophisticated simulations of physical reality, potentially offering new tools for exploring the behavior of exotic space-time configurations too complex for analytical solution. Quantum computers, still in their infancy, might eventually provide computational capabilities for modeling quantum gravitational effects relevant to the physics of time travel. Neuroscientists and cognitive scientists continue to investigate how our brains construct our subjective experience of time, potentially revealing ways in which that experience might be modified or extended. Understanding the neurological basis of temporal perception might someday enable experiences functionally similar to time travel, even if physical displacement through time remains impossible. This multifaceted research represents a collaborative human endeavor to understand one of the most fundamental yet mysterious aspects of reality. While practical time machines remain firmly in the realm of science fiction for the foreseeable future, the scientific exploration of temporal physics continues to yield profound insights into the nature of our universe and our place within it. So what might the future hold for time travel research and potential technologies? Several possibilities emerge from our current scientific understanding. First, we might eventually develop technologies for substantial future-directed time travel through relativistic effects. While the engineering challenges are formidable, they don't appear to violate any fundamental physical principles. Perhaps centuries or millennia from now, sufficiently advanced civilizations might develop propulsion systems capable of accelerating macroscopic objects to velocities where time dilation becomes significant on human timescales. Similarly, habitats capable of safely exploiting the gravitational time dilation near black holes or other massive objects might enable dramatic temporal jumps into the future. Second, advances in biological and medical technologies might enable functional equivalents of time travel without requiring exotic physics. Perfected suspended animation or cryopreservation would allow individuals to skip over intervening years while aging minimally, effectively traveling to the future from their subjective perspective. Radical life extension or biological immortality would enable natural witnessing of future eras that would otherwise lie beyond individual lifespans. While these approaches don't constitute time travel in the physics sense, they would achieve similar experiential outcomes. Third, increasingly sophisticated simulation technologies might eventually create experiences functionally indistinguishable from actual time travel. Advanced virtual reality, direct neural interfaces, or technologies beyond our current imagination might someday generate immersive reconstructions of past eras or projections of potential futures, so convincing that they would be experientially equivalent to temporal journeys. While such simulations wouldn't constitute actual displacement through time, the subjective experience might be identical from the participant's perspective. Fourth, deeper theoretical understanding of time might eventually reveal possibilities currently beyond our conceptual framework. Just as Einstein's theories revealed capacities for temporal manipulation that would have seemed impossible under Newtonian physics, future theoretical breakthroughs might uncover aspects of temporal reality that open new pathways for time travel or related phenomena. The reconciliation of quantum mechanics and general relativity into a comprehensive theory of quantum gravity represents a particularly promising frontier for such breakthroughs, potentially revealing fundamental insights about time's nature. Fifth, we might conclusively determine that certain forms of time travel are fundamentally impossible, not merely technically challenging, but prohibited by the basic structure of reality. If Hawking's chronology protection conjecture is proven correct, for instance, we would establish that closed time-like curves cannot form under any physically realistic conditions, definitively ruling out travel to the past. Such a negative result would represent an important scientific advance, constraining the range of possibilities and focusing research on more promising avenues. These various possibilities aren't mutually exclusive. We might develop limited capabilities for future-directed time travel through relativistic effects while conclusively proving the impossibility of past-directed travel. We might create increasingly sophisticated simulations of temporal journeys while continuing to pursue more exotic physical approaches. We might extend human lifespans dramatically while simultaneously developing technologies for relativistic flight. The ultimate future of time travel research likely involves parallel advancement along multiple pathways, with different approaches yielding different capabilities and insights. Whatever specific developments the future holds, the scientific exploration of time travel possibilities will continue to yield valuable insights, even if practical time machines never materialize. Research into exotic space-time configurations advances our understanding of gravity and the structure of the universe. Investigation of closed time-like curves and their paradoxes deepens our comprehension of causality and information flow. Exploration of time's fundamental nature at the intersection of quantum mechanics and general relativity pushes forward the quest for a unified theory of physics. Beyond these scientific benefits, the contemplation of time travel expands our philosophical and conceptual horizons. It challenges us to think beyond our ordinary temporal perspective, to consider reality from viewpoints outside our immediate experience, to question assumptions that seem unquestionable in everyday life. This conceptual stretching has value regardless of whether physical time travel ever becomes possible. Time travel also serves as a powerful vehicle for exploring ethical, social, and existential questions. It invites us to consider our responsibilities to past and future generations, to reflect on the nature of choice and determinism, to contemplate what aspects of reality we would change if we could, and what we must accept as immutable. These explorations enrich our understanding of ourselves and our place in the temporal fabric of existence. For all these reasons, the scientific and philosophical investigation of time travel will likely continue as long as human curiosity endures. The questions it raises touch on the deepest mysteries of physics, consciousness, and reality itself. The answers, whether they ultimately enable practical time travel or conclusively demonstrate its impossibility, will transform our understanding of the universe and our place within it. As we conclude our journey through the physics of time travel, it's worth reflecting on a profound irony. While we might never develop the capability to physically travel back in time, we have developed remarkable abilities to reconstruct and understand the past. Through archaeology, geology, paleontology, astronomy, and other historical sciences, we can determine what happened billions of years before human existence. The cosmic microwave background radiation allows us to observe the state of the universe just 380,000 years after the Big Bang, some 13.8 billion years ago. In a very real sense, we're already time travelers, observers able to witness the echoes of cosmic history across vast temporal gulfs. Similarly, while we cannot physically leap into the future, our mathematical understanding of physical laws allows us to predict with remarkable accuracy how systems will evolve over time. From the orbits of planets to the decay of radioactive isotopes, from climate models to cosmic evolution, we can project future states based on present conditions. These predictions aren't perfect. Complexity and chaos impose fundamental limits on forecasting, but they represent a form of future seeing that would have seemed magical to our ancestors. These capabilities for understanding past and future without physical time travel suggest an important perspective. Perhaps the ultimate goal isn't to move our bodies through time, but to expand our minds across it, to develop ever more comprehensive understanding of reality's temporal dimension from our fixed position in the present. This intellectual time travel, already well advanced and continuing to develop, may prove more valuable than physical displacement through time could ever be. The quest to understand time, whether it flows or stands still, whether it's fundamental or emergent, whether it can be traversed or only experienced moment by moment, represents one of humanity's greatest intellectual adventures. From Einstein's revolutionary insights to contemporary explorations at the frontiers of quantum gravity, from philosophical debates that have raged for centuries to cutting-edge neuroscience. Revealing how our brains construct temporal experience, this quest has continually expanded our understanding of reality and ourselves. Time remains in many ways the most mysterious dimension of our existence, the background against which all experience unfolds, yet itself resistant to direct examination. We cannot hold a moment of time in our hands, capture it in a laboratory apparatus, or observe it directly. We can only measure its effects, track its passage, and construct theories about its fundamental nature. Perhaps this elusiveness explains our enduring fascination with time travel. To master time, to move through it at will, rather than being carried along by its seemingly inexorable flow, would represent the ultimate transcendence of human limitation. It would transform us from passengers on time's one-way journey to navigators charting our own temporal course. Whether such mastery ever becomes possible remains an open question at the frontiers of physics. The theories, possibilities, and limitations we've explored throughout this documentary represent our current best understanding, a snapshot of ongoing scientific inquiry that continues to evolve with new discoveries, experimental results, and theoretical insights. What seems clear is that time, far from being the simple, uniform flow of our intuitive understanding, is a far more complex and subtle aspect of reality. It stretches and compresses depending on motion and gravity. It intertwines with space in a four-dimensional continuum. It may emerge from more fundamental quantum processes rather than existing as a basic framework. It might even be, in some deep sense, an artifact of our consciousness rather than an independent feature of external reality. This complexity doesn't diminish time's importance in our lives, but rather enhances it. The more we learn about time's true nature, the more remarkable it appears, and the more precious our limited span of it becomes. Whether or not we ever develop the capability to travel through time, we can surely learn to travel more mindfully within it, appreciating each moment of our brief but wondrous journey through the cosmic timeline. The human fascination with time travel will undoubtedly continue, inspiring scientific research, philosophical inquiry, and creative exploration in fiction and film. Perhaps someday, travelers from our future will look back on this era with its nascent understanding of temporal physics and its early speculations about time machines as the beginning of a journey that eventually led to genuine mastery of the fourth dimension. Or perhaps they will recognize that certain forms of time travel remain forever beyond reach, constrained by physical laws deeper than we currently comprehend. Either way, the quest to understand time and explore the possibilities for traversing it represents one of humanity's noblest intellectual endeavors, a collaborative effort spanning generations and disciplines to comprehend a phenomenon that shapes every aspect of our existence. In pursuing this understanding, we enrich not only our scientific knowledge, but our philosophical wisdom and our appreciation for the temporal context of our brief but significant place in cosmic history. As we reach the end of our exploration, we find ourselves back at the beginning, in the present moment, the only point from which we can act, create, discover, and connect. Whether time is a river carrying us inexorably forward, a landscape we might someday learn to navigate in multiple directions, or something more subtle and complex than either metaphor suggests, our experience of it remains central to the human condition, and our quest to understand it, to probe its mysteries, test its limits, and perhaps someday master its flow, continues as one of the great adventures of the human mind. We leave you with the words of physicist John Archibald Wheeler, whose wisdom encompasses both the scientific challenge and the human significance of our temporal existence. Time is nature's way of keeping everything from happening at once. In the space between the simultaneity that Wheeler references and the eternal nothing that would exist without time's ordering principle, we find ourselves, temporal beings, seeking to comprehend the very dimension that makes our existence, our consciousness, and our quest for understanding possible in the first place. Perhaps there's a certain perfection in that circularity, in being temporal creatures striving to understand time itself. Whether or not we ever achieve the capability to physically travel through time, the intellectual journey of understanding it transforms us nonetheless, expanding our perspective beyond the narrow window of our individual lives toward a more comprehensive vision of our place in the vast temporal tapestry of cosmic existence. And in that expanded awareness, we might find something more valuable than physical time travel could ever provide: a deeper appreciation for our brief but significant role in the ongoing story of a universe coming to know itself across the magnificent sweep of cosmic time.